Morning, everyone. We'll just give it one more minute before we start, just to let everybody join the session. Okay, good morning, everybody, and welcome to the Research Methods for Solar PV 2023 workshop. This is the 10th edition of the annual Super Solar PV training workshop. The idea being to train early career researchers on different ways of characterization and analysis of PV cells. Yeah, today we've got some brilliant speakers, 5 different speakers all across the world joining us to talk about all things from characterization, analysis, and fabrication of PV. So we'll kick off today with Dr. Amalka Jawadena from University of Surrey, talking about organic solar cells. Thank you, Amalka, for stepping in. We had to make a last-minute change due to unforeseen circumstances, and Amalka will be giving us a brilliant talk on organic PV, followed by Dr. Hugh Nugent from Australian National University on spectroscopy for photovoltaics. Then Dr. Katie Shanks from University of Exeter for optics for PV. And again, thank you, Katie, for joining us all the way from Australia this time. Then we'll have a 1-hour lunch break, followed by our afternoon session, which will be George Koutsarakis from NPL on IV measurements for PV, and Dr. Silvana Oviet from NREL on bifacial PV modeling to finish us off at the end. So before we kick off, just a quick summary of SuperGen and Super Solar. So this is free to join and it's open to all. There are currently around 750 members, students, academics, and industry. There are regular newsletters with updates on Super Solar events. And please keep up to date with those because there are lots of opportunities there. Funding for international and industrial secondment projects. Again, very useful. Support to attend Super Solar events and attend international conferences. And free places at some of the other UK events for Super Solar members. So you can find the link here for joining the Super Solar network. So one of the things we wanted to bring attention to is the Super Solar Childcare Fund. So this is intended to assist researchers, both students, postdocs, and academics throughout UK universities to help attend Super Solar organised events, and they will sponsor up to £500 towards childcare costs to attend these. So please do make use of this opportunity. And again, you can find out more about this on the website. Finally, just to advertise a couple of events before we move on to today's workshop. So we've got photovoltaics in the circular economy event on the 7th of June. Again, a free webinar. Please register for this, a brilliant event focusing on a critical topic in our area on recycling. As we head towards multi-terawatt systems, I think there will be a lot of strain on recycling and pressure and looking at how we can actually make this a lot more sustainable. So please sign up for this brilliant event. The last event to advertise is the PVSat 17 and Super Solar conference. So this year we've joined up to do an in-person conference at the Institute of Physics. That's 26th to 28th of June, 2023. Please use this link to register for the event. We are still open for late abstracts, but we've had a great amount of submissions come in, and we hope to advertise the full program shortly. But early bird registration is, I think, 16th of May or 9th of May. So please do use the link and register early. We look forward to welcoming you all at the Institute of Physics in June. So let's kick off our workshop today. So I'll pass over to our first speaker. Let me just stop sharing. Yeah, I'll pass over to Amalka. Could you share your screen?
Okay. Hopefully you should be able to see my screen now. Yeah.
Yeah, brilliant.
Great. Right. Thanks, Taz. So I'm going to be, I know that the overall theme of this workshop today is mainly on focusing on the characterization technique. So I'm going to be talking about organic solar cells. But as part of this, I'm hoping to cover some of the early developments in the field, and to some extent, I'm not going to go into full detail in many of these, but some of the challenges that we've faced in characterizing these organic solar cells accurately. What's taken place, I would say, since 2016, the emergence of new molecules and how these new molecules are opening up applications into applications in new areas, which we really didn't consider about 15 years ago. So areas like indoor energy harvesting, applications in greenhouses, potential space application, radiation sensing and imaging. And the characterization techniques that are really relevant for some of these emerging applications will to some extent tie in with the rest of the speakers within this workshop. Right. So semiconductors for photovoltaics, just to give you a brief idea on the types of materials that's normally used in PV, which I'm sure most of you will be aware of some of these. So the workhorse of photovoltaics has really been crystalline silicon. And in terms of commercial applications, crystalline silicon still holds pretty much a large portion of the market. When I started working on organic solar cells, kind of the dream was maybe OPVs will one day take over and replace crystalline silicon as a low-cost alternative. But crystalline silicon has seen significant progress in terms of cost reduction and improvements in efficiency at module level, and it hasn't really moved away. There's other technologies like gallium arsenide and 3,5 multi-junction solar cells, which are more relevant to space applications, I would say, primarily in relation to the radiation hardness and the cost in fabricating these sort of devices. All of these crystalline silicon 3,5 technologies are vapor phase. And then there's more commercial thin film technologies like amorphous silicon. So if you look at your calculators and some of the watches, they incorporate a small amorphous silicon solar cell for energy harvesting and powering small electronic applications. There's technologies like cadmium telluride, which is also commercial, SIGs, and more recently, there's been growing interest on other materials like perovskite for PV applications. And in some sense, the drop in the interest in organic solar cells was tied in with a growth in interest in perovskites, which has seen a tremendous jump on its own as a single junction technology, and more recently in tandem solar cells. Organic solar cells have started to compete again to some extent with perovskites, but the target markets are different now for PVs. There's been development in dye-sensitized solar cells, which is sort of the precursor for perovskite technology development, and there's other activities on quantum dot-based solar cells. Right, so early days of organic semiconductors. So the Nobel Prize in Chemistry in 2000 was jointly awarded to Professor Alan Heeger, Professor Alan McDermid, and Professor Hideki Shirakawa for the discovery and development of conductive polymers. So this work probably, if you look back, developed in the late 70s, which really was the precursor for developments in organic solar cells and OLEDs, organic light emitting diodes, which you now find in most of the display technologies like in mobile phones and TVs. As always with many of these developments, there's points of controversy. So there's this interesting link which I found, which claims that although Professor Heeger and the others are credited with the discovery and development of conducting organic molecules, there was prior work published in this area, which seems to have, to some extent, not been considered. So there's a bit of controversy there. The original, well, while the photovoltaic effect in organic materials was demonstrated a long time ago, the precursor to what we consider as the modern architecture in organic solar cells can be dated back to this paper in 1985, where what you might say we can consider it as a two-layer structure. So copper thiocyanine and this perylene tetracarboxylic derivative were stacked on top of each other to result in, at that time, a more efficient photovoltaic device. So the device architecture is shown here. It's got glass as the substrate and indium oxide as the transparent conducting oxide, then the PV layer and a silver top contact. Just this point sorted. Yeah. And then they were able to get very decent, well, at the time, decent currents and voltages for this type of an architecture. The limitations of the original organic solar cell architecture was that, unlike, say, for example, crystalline silicon solar cells, the charge generation process is not as straightforward. So the light absorption by the organic molecule first generates a species called an exciton, which is really a bound electron and a hole pair that's bound together. They're not separate free carriers. So they need to be separated to result in the electric current that we can measure. And within this type of an architecture, the separation of this exciton into an electron and a hole happens at this interface between the copper thiocyanine and the PV molecule. So if you think of just two layers, that leaves a very small contact area between the two layers to really generate the photocurrent, which really results in this very low currents observed. In 1992, there was this breakthrough paper in relevance to photovoltaics, where ultra-fast charge transfer was observed from an organic molecule to C60. And the techniques that were used at that time were transient absorption spectroscopy in showing that this ultra-fast charge transfer happens. And it still remains one of the key techniques if you want to look at how efficiently the molecules transfer, how the exciton dissociation and the charge transfer happens. And in optimizing any new molecules that are fabricated. So as we go along, we'll see that rather than just being a single molecule, the OPV community has a lot of molecules to play with, and sometimes it's too much, to be honest. The key sort of the architecture that has been used in OPVs was first described around 1995. There were two papers in sort of appearing around the same time. One was in Science, this work on polymer photovoltaic solar cells, enhanced efficiencies were a network of internal don't accept heterojunctions. So if we look at this particular architecture, I mentioned that the two layers, the copper thiocyanine and the PV layer, they are stacked almost in a planar configuration. The change from this into this bulk heterojunction architecture is that we're no longer looking at just a planar stacking. We're looking at mixing the materials in a 3-dimension, which allows a larger interfacial area to take place, to be created between this MEHPPV and C60 molecules. And that leads to a significant improvement in the solar cell efficiency. So this paper claims an efficiency of around 2.9%. One of, I would say at this point within the area of organic solar cells, there was a lot that remained not well understood. For example, how do we characterize these solar cells? What's the importance of using aperture masks in defining the active area? How leakage currents from, if you've got multiple devices on the same substrate, how energies and pixel can affect the performance that you measure in a given solar cell. And some of the measurements were not really done with a standard solar spectrum. So that could lead to varying performance metrics at that time. A second paper that appeared around the same time as this work was from the Cambridge group, efficient photodiodes from interpenetrating polymer networks. So this is really classic example of how multiple teams could be working in parallel on the same technologies. And you still see this happening where papers roughly covering the same topic appear within short time span of each other. In this one, they used MEHPPV, the same molecule as the other work by Heeger and his co-workers, but the acceptor molecule used was a different type. They did not use the fullerene derivative, but they were still able to demonstrate a fairly efficient photovoltaic performance or a photodiode behavior from these sort of architectures. Following from these early developments, one of the key molecules that emerged as what we call a donor polymer. So with organic solar cells, there's usually two classes of materials which you want to mix together to have this photovoltaic behavior. One type is called the donor molecule, which in some sense you can think of like as being similar to a p-type molecule, because most of the time the donor molecules end up extracting or transporting the holes. And then there's the acceptor molecule, which transports the electrons. The reason why we sort of call these donor molecules is that it does the main portion of light absorption, generates the exciton, and then the exciton dissociation happens at the donor acceptor interface. So the acceptor accepts the electrons while the donor donates it. One of the key challenges in this bulk heterojunction architecture, which was starting to gain prominence at this point, was how do we control this phase segregation behavior? So if you think of your device stack, we have this glass ITO going back again. And then there was this incorporation of P.PSS, which is meant to be a hole selective contact or improve the hole selectivity within this bulk heterojunction architecture. The need for the P.PSS layer really arose from the fact that when we start intermixing these molecules together, there's no guarantee that you will have a purely hole transporting material at the ITO contact end and a purely electron transporting material at the cathode end. So that necessitated the incorporation of charge selective contacts at the two ends of the devices. And this P3HT molecule really started gaining prominence as one of the more popular molecules in organic solar cells, almost like a first generation molecule, if you think of it, which was then incorporated with PC60BM initially and then PC70BM to improve the photocurrents and the voltages. So like I mentioned, one of the key challenges was how do we really control the phase separation properties when we were using these P3HT molecules. And there were again two works that came along pretty much close together, which suggested that if we were to deposit these materials usually via spin coating, and then rather than quickly allowing these materials, the films to dry out by putting them directly on a hot plate, if we were to keep them in a solvent-rich atmosphere, it creates the necessary conditions to form the right size of phasors and to improve the photocurrents that we obtain through the mix, through optimizing the blend within the device volume. The prominence of P3HT lasted till about 2008, and there were not really many molecules that could surpass the performance of P3HT and C70 based derivatives in terms of organic solar cell performances. So the efficiency is kind of saturated to about 4%, 4.5% in optimized cases with different architectures. Around 2008 and 2009, there was a surge in interest in synthesizing new molecules. In terms of replacing P3HT, there was not much interest or a push towards replacing the C70. And one of the earliest molecules to emerge was this molecule called PCD-TBT, a carbazole-based molecule, which at the given time pushed the efficiency from 4% to about 6.5% by optimizing the structure through the incorporation of optical spacer layers, metal oxide charge transport layers, different ways of doing it. One of the key attractions of PCD-TBT was that unlike most other organic molecules, this molecule was really stable, even under ambient conditions. And the projected lifetimes, I recall, at that time were around 20 years. I say the projected lifetime because nobody actually ended up doing the full stress testing as we do nowadays. This has been superseded, well, this was superseded by a newer class of molecules. As you can see, compared to the very original P3HT thiophene-based molecules, things started getting more complicated with different chemical modifications being done. It's not only this monomer that was being modified, even the side chain modifications were shown to improve the device efficiency. So one of the developments in 2014 involved replacing PCDTBT and some of the other molecules that were giving around 7-8% in the device efficiency was this PFFBT40 -2OD, a long name. I think we used to call this PC11 or something because the name was too long. And that allowed a more red-shifted absorption and improving the photocurrent in the same process. Moving on from that, around 2016, so people were up to this point looking to developing new donor molecules in terms of improving or the absorption. In 2016, there was sort of a resurgence in OPVs in looking to develop new acceptor molecules. C70 derivatives had been the mainstay, but one of the key challenges with C70 or PC70BM had been their intrinsic degradation, or what is understood at the moment is dimerization of these molecules, which leads to an initial 20% drop in the efficiency before it stabilizes off. So in 2016, there was this introduction of a new class of molecules called based on this IDTBR structure. And you change again the side groups, which allows changing of the molecular packing and in some instances the band gap. What these molecules allowed was a more stable device architecture and better performances to be realized even with P3HT. So if you recall, P3HT PCBM would start off around 3.5–4% efficiency, whereas if the PCBM is replaced with one of the IDTBR derivatives, the efficiency is pushed up to around 6%. And the degradation time in air increased with these new acceptor molecules. Now, this is not the case with all acceptor molecules, but in the case of IDTBR, that was at the time identified to be quite a promising molecule for pushing this activity further. Since then, there have been a load of other molecules that have appeared. So one of the newer donors that we have also been working on here at the University of Surrey is this PM6, and an acceptor is Y6. So this allows a more redshifted absorption spectrum or photocurrent generation in these solar cells, allowing the photocurrents really to be pushed beyond the 25 milliamps per square centimeter mark. Now you'll see that over here, the Y6 acceptor is now absorbing in the infrared region. So unlike the classical model where we really don't consider a significant photocurrent contribution from the PCBM, in these newer class of bulk heterojunction devices, the acceptor contributes a significant portion to the photocurrent generated. And one of the key attractions is that we can now push the device thicknesses above 100 nanometers. So normal thicknesses that we would work with organic cells tend to be around 80 nanometers or 220 nanometers thereabouts to minimize the optical absorption. But the newer molecules have allowed the pushing of these thicknesses to what I would say more manufacturing friendly using printed techniques. More recently, so organic solar cells are now, they've now gone beyond really the 18% efficiency mark. So there are now newer acceptor molecules like these L8BO, L8HD, and L8OD based derivatives, which have allowed, so the L8BO derivative has allowed the efficiencies to go above 18%. And if the PM6 is partially replaced with other donor molecules, some of the newer classes like what we call D18, they allow efficiencies closer to 20% to be realized now. So you can see that the efficiencies have now pushed to quite an extent where it's becoming, to some extent, competitive with some of the perovskite devices. I wouldn't say in every sense of the word competitive, but there is further scope for improvement here. Skip that. So this is, so in the earlier developments, I was only referring to the use mainly of one donor, one acceptor type architecture. there has been the case of having multiple donors and multiple acceptors. So in this class of devices shown here, so PM6Y6 in general gives about a 15% efficiency on average. But if you add a bit of PCBM, the efficiencies can be pushed a bit further into the 16% mark. That's mainly due to a better exciton dissociation, and sometimes you can plug in a bit of the photocurrent loss in this blue-green region with the incorporation of this PC70BM molecule. The more newer architectures tend to push this even further, in some cases using 4 molecules, so 2 donors, 2 acceptors, which is really pushing the limits of how easily can we control the phase segregation in these class of materials. So some of the key take-home points in terms of the materials is new donors and new acceptors have provided a pathway towards generating high efficiencies, but you have to be always careful on how you select these materials, whether it's for a tandem architecture, single junction architecture, and most of the work really has been on single junctions in these kind of devices. But you have to also consider additional aspects like stability and scalability. So stability, with the efficiencies going further, stability becomes a key point, which really the field needs to consider, particularly under selecting the proper stress testing conditions, at least for AM1.5G operation. So I'm going to move on into some of the application areas for OPV. So the first one that immediately comes to mind with OPVs is indoor energy harvesting. Now, this is something I kind of incorporate in my teaching in renewable energy devices beyond Moore's law, which is not really beyond Moore's law, if I'm honest. But the idea is that, as we all know, Moore's law has pushed the miniaturization of most electronic components. And at the same time, what it's really allowing is the reduction in the power usage has allowed self-powered devices to emerge. So going forward with the emergence of 5G and 6G technologies, we really have to consider how do we harvest energy from ambient conditions in powering portable electronic devices. So this could be, for example, different sensors, monitoring air quality, for example, or health monitoring. Things like that would really benefit from ambient energy harvesting technologies. Now, unlike the AM1.5G spectrum, which we use almost routinely to characterize solar cells of most types, the indoor spectrum poses a different problem in terms of a use or testing of devices. The issue that we have is there's different kinds of spectrums that can be used in characterizing these devices, which at the moment creates a fair bit of confusion on how do you really measure different types of devices. So for example, if somebody says my solar cell architecture is 40% efficient under indoor conditions, is it really comparable to another report says that my cell is 32% efficient? So there's really a growing need for a development of standards for testing of these organic solar cells and any other solar cell architecture for indoor conditions. Now, in terms of OPVs, what are the things that we need to consider if we are to develop these for indoor energy harvesting? So the first thing is what's really the spectrum that we want to tailor these OPVs for. So as the spectrum changes, we have to select different classes of materials and different light levels, really, in order to make sure that we've got the right combination of materials to generate the best power output. Another key challenge with indoor energy harvesting is that the currents that are generated are much lower compared to, for example, the AM1.5G spectrum. And at this point, the leakage currents from the solar cell, controlling that becomes relevant almost to the point of what we work with in terms of X-ray detectors. Additional factors that we would need to consider is the use of non-toxic materials, potentially aesthetics, if possible. They're not, at this point, I wouldn't say they're crucial, but they will become key aspects that we need to consider. So how do we match the spectrum? So there's like I mentioned, there's loads of materials that can be used for indoor applications. Some of these are given here. So if I look at this panel here, the black line indicates the typical AM1.5G spectrum that we use when we want to compare most of our solar cells that we characterize. Then we have this red line, which corresponds to an LED that has color temperature of 30,000 Kelvin. And then there's different absorbers with different absorption spectrum, different blends with different absorption spectrum. So by tuning the composition of these different blends, we should hopefully be able to identify composition that is more ideally matched towards the indoor spectrum that we would like to use our solar cells with. Now, reducing the dark current. So this is a very nice example of why reducing the dark current becomes important as we consider the indoor spectrum. Apologies for the poor rendition of the figure, which looks a bit blurry here. But if you look here on the panel on the left here, the red dashed line is PM6Y60 tested under AM1.5G condition, which what most of us would normally do. But as we go to an indoor spectrum and change the light levels, we can see the photocurrent contribution reducing. And if we have a fairly significant dark current, we would lose out most of this photocurrent because of recombination effects. We see this more drastically in terms of this combination of material here. Now, going from this panel on the left to the right one, the only difference in the device performance is the use of this particular blocking layer within the device. So PDINO or PDNO is used to modify the cathode contact to allow better electron selectivity. The similar with PFN. So what this really tells is we need to look not only at the blend itself, but also we need to consider what's the contribution from the charge selective layers in terms of minimizing the dark currents of these devices. So the key take-home points in terms of indoor applications, we shouldn't really be focused only on mounting on building, but there are potential number of other spaces where we can incorporate these organic cells for indoor applications, for example, this lampshade here. And then we need to carefully consider the spectral response that's required for these devices and look to minimize dark currents and potentially be inspired from the developments that's taking place in organic X-ray detectors. Moving on to another application space in greenhouses. This is to some extent, the use of agrivoltaics is not new, but the use of organic solar cells has been growing in interest over the last 4 or 5 years, particularly with the development of new molecules, and I'll shortly tell you why. Now, why do we need to incorporate solar cells or organic solar cells? One is we would like to minimize the heat that is going into our greenhouses. That helps to reduce the evaporation that takes place and helps to maintain a constant humidity level, and at the same time allow us to generate some electricity from these spaces. So design criteria for OPVs in greenhouses. So plants normally absorb below 1.7 EV or below 730 nanometers in terms of wavelength. And with the newer organic semiconductor molecules, the OPVs can be tuned to absorb outside of this window. So it almost becomes transparent to the blue-orange region of the solar spectrum while absorbing at much narrower wavelengths. The key advantage is that, of course, no additional land requirement, and to some extent, it bypasses restriction on grid installation. But in terms of a device architecture, what we normally have with an OPV is we have a transparent contact on one side and a reflecting back contact on the other side. But going into greenhouse applications, we would need to modify the device architecture so that we have transparent electrodes on both sides so that we have light transmitting into the greenhouse, which would mean that not only are we forced to modify the bulk heterojunction architecture, but we have to also consider how do we optimize the device thicknesses if it's just a single pass in terms of the device thickness. Now, this is, I would say, a fairly messy diagram. But it does show how the number of molecules that's available to be used in these spaces. I've almost lost count of how many molecules that I've shown here. But if you ask anybody who's working in the area, they'll probably say, especially a chemist, that we can synthesize molecules now that absorbs outside of the region where our plants generally absorb. So this is really a good thing in terms of a new application space for for OPVs, that is for greenhouses. But again, we have to carefully consider how do we tune these and optimize the device architectures. Now, one thing we can do is, I'll quickly cover this, to modify of device architecture, is to change what's called the heteroatom that's used. So for example, this X site over here within this molecule can either be carbon, or in some instances, it can also be a silicon atom. And just by the simple change in the molecular architecture, we can tune the absorption of the molecule. So for example, in this particular molecule, COTIC4F, we see a more redshifted absorption. That is, we get a better transmission in the wavelength region for plants if the X site is occupied with carbon in place of silicon. And a few key take-home points of OPVs for greenhouse applications. So we need to really consider tuning of the blend to allow for transmission in the visible region. And again, we still have the same challenge of reducing the dark currents, particularly as the band gap reduces. Something I'm not so sure on is whether there's room for multi-junction cells in terms of greenhouse applications. It might be useful, it might be not, but I have yet to see anything done in this regard. An emerging area of interest, which has really taken off with perovskites, is space applications. So OPVs in space is another area that there is some limited activity. And unlike terrestrial applications, when you send solar cells out into space, there's a number of other stresses that can degrade the device quite quickly. So a key one is there's a lot of UV when you send these solar cells into space. What's the stability of our semiconductors under UV? Then there's high energy particles like protons, electrons, neutrons in very high fluxes, which can cause damage not only to the semiconductor material, but also to the substrate itself. So for example, the typical glass substrates that we use for terrestrial applications don't really work in space applications, because under proton absorption, what happens is they form what's called color centers, and they start limiting the light that's transmitted. And then there's large temperature fluctuations. So in space, the solar cell temperature, you could be going anywhere from 100 degrees to minus 100 degrees. So whatever architecture that's fabricated for space applications must be able to withstand these temperature fluctuations that takes place quite frequently. Current technologies are based on multi-junction designs, mainly 3.5s, but there's a growing interest on looking at new flexible architectures that can be low cost and high efficiency. And this is really where the attraction of OPVs and perovskites are, because they can be made on flexible substrates quite easily at low cost. But are they really radiation tolerant? Now, this is an example of a study done on proton energy deposition in an organic solar cell architecture. So if we look at the figure here, this is what's called a stream simulation. It simulates the energy that's deposited for a given ion energy. So in this case, it's for 150 keV proton. And what we see is we have the silver back contact here, that's a reflective back contact. We have a whole selective molybdenum oxide, then the PTB7TH PC70BM organic blend, a zinc oxide layer, and an AZO transparent conducting oxide, and a quartz substrate. And the simulation, it's not the ideal way of simulating this, but the energy has been simulated so that it's incoming from the silver end. In a space application, you'd want the light coming in from this end, which would mean that the proton energy really should be simulated to be incident from the quartz substrate end. But the key point is that if we simulate sort of the target depth at which most of this energy is deposited, we see that as the proton energy increases, so a 10 MeV proton, which you can find in space, needs about 1 millimeter thickness for it to deposit most of its energy. So this peak here is where most of the energy is deposited with regards to a proton. If we take something like a 500 keV proton, a 10 micron, the energy is deposited at around 10 micron thickness. And if we take a 50 keV proton, within a micron, the entire energy is deposited. So when we do these simulations, we actually have to consider which side the energy is coming in from, what's the influence of the thickness of these substrates, and how do they contribute to where this peak energy is being deposited. So that could influence how fast these solar cells will degrade. And in terms of stability of OPVs under proton irradiation, what we've seen so far, or what's been reported so far, is that protons actually tend to degrade quite fast under proton irradiation at fairly high fluences relevant to space conditions. However, there's still a bit of ongoing debate, particularly in relation to these new thin film technologies for space applications, and what's really the test conditions that we should be using for degradation studies. Should we be using a 68 MeV photon or proton, or do we use the 150 keV proton? So there's a bit more to study in depth here, and whether there's room to optimize the device stack such that the maximum energy deposition point, this point, whether it can be shifted out of this device active area. Just a quick coverage on what actually leads to this degradation. One of the key factors, what we think is happening, is the proton irradiation leads to a trap formation within the absorber itself, which leads to charge trapping, and as a result, a quick degradation in the EQV that leads to losses in the PCE. So key take-home points for OPVs in space applications: high energy particles could potentially damage OPVs, but might be able to mitigate that by carefully tuning the architecture. But in doing so, we must consider what's the energy of the particle, what's the flux, and how the overall stack affects the performance. And then moving on to a related area, hybrid organic semiconductors, or architectures similar to solar cells for radiation sensing. To quickly give you an idea where the field is right now. So the original semiconductors used for radiation detection, solid state semiconductors, was based on silicon and germanium. Not ideal for a number of reasons. Germanium, for example, needs cooling in order to get any reasonable detection. Silicon doesn't have a strong absorption. So what has happened is amorphous silicon photodiodes are often coupled with what's called a scintillator, which absorbs the X-rays and generates visible light. That used to be a popular architecture to some extent. It's still used industrially. Then there's 3-5 semiconductors that are being tested for X-ray detection application. More recently, there's been a development in the use of cadmium telluride and cadmium zinc telluride for X-ray detection. Historically, these did struggle in terms of obtaining stability in terms of detector performance, which have been overcome and are gaining commercial ground right now. And there's a growth in the interest on the use of organic semiconductors. So for example, single semiconductor materials like pentacene for X-ray detection. And we've looked at the use of adopting organic solar cell architectures and modifying them for X-ray detection. So quickly go through this. So this is an architecture that we've developed at Surrey, where we've taken the P3HT PC70BM blend, but increased the thickness to be 10 to 50 microns, and in some cases 1 millimeter by changing the processing conditions. But to stop X-rays, we need an element that has a high atomic number. So we ended up incorporating bismuth oxide nanoparticles into this blend, which absorbs the X-rays, generates free electrons and holes. And we think that the hole is transported away by this P3HT and the electron is transported by the PCBM. Now, the advantage of this particular architecture, unlike most other X-ray detectors, is this detector, for reasons that's not clear yet, can detect anything from 1 kV X-ray right up to 15 MeV. Now, 6 MeV to 15 MeV is what's normally used in cancer therapy. And there's not a lot of materials that can be used for dose measurements at that end. So rather interestingly, we found that these organic semiconductors can actually be used for detection at those high energy ends. And there's the potential for conformal functionality. Now, one of the challenges that we did struggle here is that the dark currents were quite high. So if we think of an X-ray detector, we normally want a 1 to 10 picoamps per square millimeter. And we were getting about 1 to 10 nanoamps per square millimeter levels, which is quite high than what we required. What we did find out was that when we were fabricating these devices, the phase segregation again plays a key role. So instead of using, if I go back, a PEDOT PSS layer at this end to form the whole selective contact. So we have a substrate, PEDOT PSS, and our blend which absorbs the X-rays, and then an electron selective contact and the top contact. If we flipped the device architecture, we can achieve dark currents that's more in line with the industrial requirement without losing a lot of the other advantages like sensitivity or broad energy range, although we did lose a bit of the X-ray detector sensitivity. But going beyond this, we've started to look at how do we fabricate curved X-ray detectors. Now, why do we want to use curved X-ray detectors? If you think of sort of the old days of X-ray imaging, what people used to use was sort of X-ray films. That's almost like photographic films, but you could wrap it around a curved geometry and obtain an image. That feature was lost as the community started moving towards solid state detectors like cadmium telluride or more for silicon photodiode based X-ray detectors, because these are rigid in nature. Moving into organics offered us to relook at this and start to see if we could develop curved detectors similar to film, but combine the characteristics of something like cadmium telluride or amorphous silicon. So one of the industrial collaborators calls this electronic film because we combine properties of both technologies. And one aspect we were looking at in terms of optimizing these architectures for curved detectors is the tuning of the molecular weight. So what we did find out was that as we increase the molecular weight of the semiconductor, it actually allows us to form curved architectures without the detector fracturing. And we could bend these devices up to a couple of millimeters easily and obtain reproducible performances. So some of that work is actually outlined within this manuscript here. So this is an example of a curved detector that we fabricated. So this one is about 2 millimeter radius. We went even further in terms of the curvature, below 1 millimeter, if I remember right. But unless the molecular weight is carefully tuned, you find that the devices can fail by easily delaminating off the substrate. So this is some of the measurement results on these curved detectors. So as you can see, we've gone to a fairly low radius of curvature. But as the radius of curvature decreased, we did observe an increase in the sensitivity, which we don't really understand at the moment, but presumably this is because of the change in how the packing is within these detectors. A few key take-home points on organics for X-ray detectors. They are more tolerant to X-rays than other high-energy particles like protons. So we've exposed this to 6 MeV X-rays and haven't observed for very long durations and haven't observed any significant degradation in these devices. Unlike OPVs, organic X-ray detectors need to be thicker. So we're thinking anywhere in terms of 50 microns to a millimeter. So careful consideration on how do you fabricate these devices, how do you scale them up needs to be taken into consideration. And if we were to think of X-ray imaging, things that would potentially be of interest is, do we have the response speed? Can it respond as fast as current X-ray detectors in the market? Does it have the sensitivity and resolution to compete with those? Just a few final points to wrap up this talk. As you can see, OPVs has the potential to impact diverse range of applications. We're no longer thinking just grid applications. There's loads of applications that's worth looking at. So all problems are interesting. Not everything is important. So make sure if you're interested in working in this area, that you pick the right battles and challenges to address. Thank you.
Brilliant. Thank you very much, Amalka. That was a wonderful talk, very comprehensive, and you covered a lot of different topics, which I think are very useful for our audience. We've had lots of questions come in. I've got a list of them here as well. But to kick off, we've had one question regarding stability, and is stability a more meaningful parameter regarding the impact of OSC research compared to when you're comparing advances in efficiency? So is it better to be looking at actually stability over efficiency when you're looking at this research field?
It's a very interesting question. I think we are, so if we look at how the developments that's taken place, we're now at the stage where OPV efficiencies are approaching 20%. I don't think every lab is able to achieve 20%, but that in effect means we now have a handle in terms of the type of molecules that we should be looking at in pushing the field further. So as the efficiency goes further, it becomes more meaningful to look at the stability, particularly because you don't want to push the efficiencies. Let's say, hypothetically, we can get up to 25%, which may or may not happen. But if you base those developments on this class of molecules, and then if you ignore the whole stability bit and you have this 25% with a device that degrades within a couple of hours, then to some extent you're missing out on the information that could be the tool for developing the next generation of molecules. So yes, looking at stability is quite important, particularly at this stage, because that could guide the next stage of development in terms of the synthesis.
Brilliant. Yeah, I totally agree. I think not just for organics, but when you're going into cell research, efficiency over stability as the first target, I think is actually very good. Stability itself comes afterwards, but pushing towards those high efficiency. It's amazing to hear that organic solar cells are over 18% now. That's really, really great news. The next question is, are there materials that can be incorporated into organic solar cells? This is for regarding the space application. Yeah, are there materials which can be incorporated into organic solar cells, absorbing the protons while creating free electron charges?
That's an interesting one. Into the organic solar cell, I would probably, the easiest way out of this challenge is not really to look at whether you want to incorporate something that shields or absorbs the proton energy, because that would mean you're trying to modify the entire OPV structure. The more easy approach as a first stage would be, how do you change the other layers within the device? So for example, simply by tuning your substrate thickness, that can change where that final peak within that energy deposition scheme ends up at. Proton absorption, I mean, perovskites have shown considerable promise in this regard. But thinner structures in OPVs might not necessarily be a bad thing, because the peak is actually going to be shifted to a point where it's outside of the device architecture. So if you carefully tune the substrate thickness, I think it's an issue that could be bypassed. We might not be able to entirely remove the proton deposition within the organic layer. Other aspects might be, which I'm not entirely sure of, is using something like a scintillator, which can absorb the proton energy and then convert that into a visible light. That is used in some of the more modern detectors used for proton beam therapy. For example, those use silicon diodes in combination with gadolinium oxysulfide. The problem there is that if you place this in front of your organic solar cell, you're going to lose a bit of the light transmission or significant provision. So it's not always beneficial doing that. The easier one is just changing the stack configuration.
Brilliant. Thank you, Marco. Another question. From a synthesis point of view, some of the more modern, high efficiency molecules which have been developed look quite complicated. How easy is it to synthesize these molecules? Do you know what type of yield you get, and can you synthesize them in larger quantities?
Ooh, that's actually a question for a chemist. I'm not in the best position to talk about the synthesis aspect, or the yield for that matter. My understanding is that one of the well, I wouldn't say challenges. If you look at, so we tend to work with organic molecules that we buy off the shelf. So most of the molecules that you'll find reported in the scientific literature, you're almost able to find them from a supplier within, say, 1 year's worth of reporting the original work. The costs generally tend to be higher than P3HT simply because the synthesis is quite complicated. Unlike P3HT, which is a more simple monomer, the stages involved are more complicated. And my understanding is that the yield is sometimes lower than, say, P3HT. So that drives the cost higher. So unless you have a dedicated chemist who has an idea on the molecular design, the better option in terms of obtaining molecules is really going commercial. And usually, if you consider the weight fraction, so some of these newer donors were using about 7 milligrams per milliliter, which is not quite a lot, which is not a lot. With P3HT, you're looking at anywhere from 10 to 20 milligrams a milliliter. So we tended to use 20 milligrams. So the costs come in different ways there. But as there is growth in the interest in the use of these molecules, what we find is the cost does go down over time.
Brilliant. I had a question about indoor PV and organic solar cells. So there's been a lot of focus lately on electronic waste and the recycling of electronic waste. Obviously, there's a lot of focus on recycling of PV in general. As we start to incorporate indoor PV into our homes for daily use of electronics, has there been much research on how much of that organic solar cell, once it degrades, you can recycle? Or is that actually an area we should really be looking at?
I think it's certainly an area worth looking at. I haven't seen much in terms of recycling OPV. There's now a growing interest on how to recycle perovskites. So definitely there's a few learnings from that we could potentially use. In terms of an organic blend, I think the key challenge is going to be, so if you think of a perovskite stack, you probably have your transparent conducting oxide on a substrate from which you can strip off most of the molecules. Then you've got the organic material, which have solubilities in different solvents compared to the perovskite. So you can easily remove those off. The challenge that we'll find with OPVs, I think, is really the blend, because you've got two materials mixed together. They almost have the same solubility. So how do we separate those two out from that mixture? Because usually the degradation is, say, for example, the PCBM has dimerized. So we would need to find a way of sort of chemically extracting that while leaving the other molecule within the solution phase. But it's an interesting challenge from a chemistry point of view, but I don't think a lot of people have looked at this.
Brilliant. Just before we finish, I think I'll bring you back to this slide that you've got open. For the young students who are just sort of starting out in this field and really are trying to pick the right battles, do you have what are your sort of key battles you think are worth exploring?
The first one is really what application space do you want to work in? Different people have different motivations for working in areas. Some people, if you're from a developing country, for example, you might want to tackle challenges that are relevant to your country. So is it that you want to look at how do we reduce the cost in the synthesis, or how do we improve the lifetime? Recycling is an interesting one. Manufacturing. How do we find alternate transport layers that control the dark currents? But in sort of deciding that, the key starting point, I would say, is have a sense of what application space that you want to work in, and then see what are the unsolved problems there. If you look in the literature, sometimes it's hard to see that there is this particular challenge. You have to sort of read the fine lines between reducing the dark currents or stability. Has anybody reported that? It's usually what's not reported there. That's what I would be looking at in terms of a paper, and see if there's a common theme that's emerging across multiple papers to see, is this worth looking at?
Then tandem space as well. Is there?
I think there's a lot in tandem space. There's not a lot being done there, but it could be an all perovskite tandem application. It could be a perovskite organic tandem. I've seen one work where organics have been coupled with, I think, amorphous silicon for tandem. So there's a lot to be done there. If it's tandem, sometimes it's easier piggybacking on an existing technology rather than thinking of the entire stack bottom up, which is what perovskites have done successfully.
Brilliant. Thank you very much, Imelka. I
Right.
think 18% OSC, there's a lot to do. There's a
Yep.
very, very bright future. And thank you for your wonderful talk and your time. There's a lot more questions in the Q&A. So please, if you get time, just you can respond to them directly. To the audience, please keep your questions coming in through the Q&A. We'll try and get through as many as we can. And hopefully our speakers will be able to answer them directly there as well. I'll now introduce our next speaker, Dr. Hugh Nugent from Australia National University. Hugh, thank you for joining us. Could you share your screen?
Okay. Can you see my screen now?
Yeah, I can see if you go to full screen.
Yeah. Right. Cool.
Can't see your yeah, maybe.
All right.
Yes.
All right.
Thank you.
Yeah. Thanks a lot for the introduction, Tas. Hello, everyone. This is Hugh Nguyen from the Australian National University. I think in the nice talk from Imelka a few minutes ago, we learned a lot about organic PV. And now we will cover more fundamental detail about the optical phenomenon inside solar cell. And the topic of my talk today is the science and applications of optical spectroscopy and imaging for photovoltaics. And this is the outline of my talk today. First, I would like to introduce a little bit about my group and myself, and then I will cover some brief background of the optical phenomenon, including the absorption, transmission, reflection, and emission. And then I move to some common methods to measure light in the semiconductor. And finally, we will look through some examples of the optical characterization for PV materials and the devices. About ANU. So ANU is located in Canberra. So Canberra is the capital of Australia. So usually we talk about Australia. The misconception is that the capital city is either Melbourne or Sydney, but actually those are the two biggest cities in Australia. But the capital of Australia is Canberra. So Canberra is just a small city. It's not very populated, so very friendly, safe, and green. And ANU is a research intensive university. In PV research, our group has around 60 staff, and we cover silicon, perovskite, and 2D materials. The available resources allows us to span from the material engineering, device fabrication, and characterization. For myself, I got a PhD degree in PV from ANU in 2016. And in 2017, I went to the US to work as a visiting scientist at NREL. And in 2018, I just came back to ANU and worked as both researchers and lecturer since then. With my old team here, I cover silicon, perovskite, and 2D materials, and mostly on the material and device characterization, and also some of the material engineering. So that's a little bit background about myself and my group. Now, we move to the main content of the lecture today. In this first section, we cover a brief background about common optical phenomena in PV materials. We will start from a very basic definition. When we have a piece of semiconductor, when you shine the light into your materials, what often happens outside the material is this: part of the incident light is reflected back, and part of it is absorbed, and if not absorbed, it will be transmitted into the other side of the symbol. And when the material absorbs the light, in many cases, it can re-emit light at different energies. And these are basically what we often see outside the material. But what physically happens inside the material is here. A semiconductor has two distinct energy bands, the valence band and the conduction band. When the electrons are inside the valence band, they cannot move inside the materials. When they jump into the conduction band, they can move freely inside the material. And the electron can gain energies and move from the valence band into the conduction band. Or free electron can lose energy and fall back into the bound state in the valence band. And the energy gaps between these two bands here, we call it the band gap. And these are very fundamental property of the semiconductor materials. When a light ray hits this material, if the photon energy is less than the energy gap, so basically the photon can either pass through the material or being absorbed by electrons, and then the electron just release this amount of energies under the form of heat. If the photon has an energy equal or a little bit higher than the energy gap, the electron can be excited into the conduction band. Now, what if the photon energy is much larger than the energy gap? So basically, electrons in the valence band are excited into a state much higher than the conduction band, and this state is not stable. Just right away, the electron will fall back into the conduction band and release the excess energy under the form of heat. So this process, we call it the thermalization process. Then after relaxing to the conduction band, these free electrons stay here for a while. If they're not extracted into the external circuit or not moving to other materials, eventually they must fall back to the valence band and they can emit photons. This process, we call it luminescence. With the luminescence process, in general, we have the band-to-band and short band gap emission. What is the band-to-band emission? The band-to-band emission happens when the free electron in the conduction band fall back directly into the valence band. And because of that, it reflects the intrinsic property of the material. So when we have effects of impurity, they can occupy the energy levels inside the material band gap, like this energy level here. Then the electron and holes can be trapped by these centers before recombining and emitting photons. So we call it the short band gap luminescence, and this phenomenon reflects the properties of the effects and the impurities within the host material. So under excitation, when you illuminate your sample, so this basic process of absorption, thermalization, and emission will happen in each volume element of the semiconductor. And this volume element will emit photons into different directions. Then the photons move toward the surface. And on the way moving to the surface, they are reabsorbed, right? Because these photons are basically still inside the material. They are not escaping out of the material yet. And at the surface, if they hit the surface at an angle larger than the critical angle, they will be totally reflected back. So there's no chance for them to escape. If they hit the surface at an angle within the critical angle, they will have a chance to escape, but that doesn't mean that they will escape. Within the critical angle, part of them can be either reflected back and part of them can be transmitted into the outside environment. So when we are accounting for this phenomenon, the photon flux emitted from the sample is given by this formula. So basically, the emitted signal from your sample is a function of the absorption coefficient, reflectivity at the front and the back, and the sample thickness. And these properties determine the absorptivity of the sample. And the emitted signal is also a function of a positive mid-level splitting, or we call it the implied open circuit voltage, a term that we often use for silicon. And these parameters, in principle, they're all correlated together. If we have a way to control and measure some of them, we can extract the remaining. Now, when we put two materials in contact, what happens? The phenomenon of absorption transmission and emission that I have described so far will happen in both materials. But now electron and holes have places to go, right? They don't just stay in the old material. And depending on the relative band alignment of the two materials, electron and hole will move to their lowest energy stage. So a comparison here. So an analogy here, you can think about electron as the water and hole as the bubble. In the plumbing system, the water always finds a way to go down, and the bubbles always find ways to move up. And electron and holes move exactly the same. In the left image here, the electron just move from the left to the right, and holes move from the right to the left, because this is the lowest energy level for holes. If we extract them to the external circuit, we will have current and voltage. So basically, we have a solar cell. This is also the principle for line emitting diode, but the other way around. We will inject electron and hole at two different terminals, and when they move across the junction, they will recombine and emit photons. When we have band alignments, as in the right image here, things are a little bit different. Now, electron and holes are still generated inside both material, but they just move from the left to the right. Because in this case, the left material is acting as a pumping substrate for the right material. And we can see that this structure, we use it a lot in 2D materials. The idea is 2D material is too thin, just a few nanometer thin. So it cannot absorb all of the photons, even the energy of the photon are higher than this band gap. So the high energy light can partially pass through it. But if the 2D material is put on top of a pumping substrate, the transmitted light can be absorbed by the pumping substrate, and the carrier generated inside the substrate can move back into the main material. So as a result, we have more carrier population inside the main materials. Okay, to summarize so far, in the physical space, this is what happened. Light hit your materials, and then it's either reflected back, absorbed, or transmitted. And when it's absorbed, if the electron and hole are not extracted, the material can re-emit light at different energy. And this phenomenon happens for each volume element inside the materials. And these photons have to survive after many processes before we can recognize them physically. So the reabsorption inside the material, the heating the surface within a critical angle, and then escape the material. And these processes can be translated into the energy space here. Absorption happens when photons with energies higher than the band gap excite electron from the valence band into the conduction band. Transmission happens when photons with energy less than the band gap cannot excite the electron. Emission happens when electrons fall from conduction band either directly into the valence band or via the defects and impurity center before getting back into the valence band. When two materials are in contact, absorption, transmission, and emission happen in both materials, but depending on the relative band alignment, we can predict where electrons and holes can move. And to model how the light is absorbed, transmitted in each material, and how it is reflected at each interface, there are different software packages available online. So for example, you can use Oppo 2 or Samsung RoBV Lighthouse to do this job. So that is some background about the optical phenomena in PV materials. Now we move to some common methods to measure light. One of the very common tools in many optical laboratories is the spectrophotometer. We use it to measure the absorption, transmission, and reflection. This is an overview of the spectrophotometer principle. In practice, there are different configurations, but the basic idea is just the same. A spectrophotometer usually consists of two parts: an exciting, unlike the excitation part, where the white light source is dispersed into different wavelengths by a monochromator and the detection part to measure the filter light being reflected or transmitted throughout our sample. To measure the light intensity, we can use an interacting sphere here, and the filter light will be scattered over different directions by the internal of the interacting sphere. And depending what we want to measure, if we want to measure the reflectance, we have to put the sample at the back of the iterating sphere. And if we want to measure the transmission, we need to put the sample at the front of the iterating sphere. And the absorption is just 1 minus the transmissivity and the reflectivity. So that's how we can use the spectrophotometer to measure the transmission, reflection, and absorption. To capture emitted light, it's a little bit different. We have two ways: the luminescent imaging or luminescent spectroscopy. So in the imaging mode, the entire sample can be excited with a light source or an electrical source. Then you just imagine like your sample here consists of an array of areas, and each one area here will correspond to 1 pixel in the chip of the camera. And inside each one area like this, it absorbs the light and emits photons in the same way as we just covered in the background section. Then the emitted light will hit the corresponding pixel inside the camera. Then we have an image of luminescent signal. And this is an example of the luminescent intensity image from a multi-crystallized silicon wafer we captured a long time ago. So in this way, somehow very similar to the way that you use a digital camera to take the photos of your friends or yourself every day. But in your photos, you're capturing the light reflected from an object. In luminescent imaging, we have a filter to reject the reflected light from the sample and only capture the emitted light. And in a standard luminescent imaging technique, we don't have spectral information. Usually we don't know where the peak of the spectrum is. We just know the intensity of each pixel inside the image. And the intensity is determined by this formula. Basically, the original spectrum emitted from a sample has to pass through some optical filters, the objective lens, and finally hit the camera. And each of these components has its own spectral response. And the final intensity of each pixel that we detect in the camera is the integration of the original spectrum emitted from a sample, the camera response, the transmissivity of the objective, and the filters. So that's for the luminescent imaging. In the spectroscopy mode, we just simply put a spectrograph in front of the detector to disperse the emitted photons into different wavelengths. We have the entire spectrum, but we don't have spatial information. And this is an example of the emitted spectrum we capture from crystallized silicon wafer. And in practice, it's possible to combine two modes into one. We call it hyperspectral imaging. And the idea is we just insert a spectrograph between the lens of the camera and the camera. Then we synchronize it with the camera. And by that, we can select what wavelength we want to detect. When we're doing that, we will have the entire image of different wavelengths. So we will have both spectral and spatial information. So basically, we get the entire spectrum for each pixel. So that's how we often measure the light absorbed and emitted from the materials. Now, let's move to some example of optical characterization for PV material and devices. First, we can utilize the luminescent phenomenon of absorptivity and reflectivity to establish many fundamental parameters for our PV materials. Under excitation, again, each volume element of the semiconductor will emit photons into different directions. Then they move toward the surface, and on the way moving, toward the surface, they are reabsorbed. And this reabsorption is characterized by a parameter we call absorption coefficient, or alpha. And at the surface, they can be either reflected back or transmitted into the outside environment. When we are accounting for these phenomena, the photon flux emitted from the material is then given by this formula here. So basically, the emitted signal is a function of the absorption coefficient, alpha, the reflectivity at the front and the back, the sample thickness, and the quasi-Fermi level splitting, or we call it implied VOC for silicon. And all of these parameters are related together. So if we have a way to control some parameter, we can extract the remaining. So that's the basic idea. Now we apply this idea on different material. We do it for silicon. We capture the Weyl spectrum from silicon at different temperature. And for our sample, we can easily measure the reflectivity at the front and the back, the thickness, the implied VOC. And based on these parameters, we can extract the absorption coefficient, alpha, at different temperatures. And the nice thing about this method is that it allows us to measure to the extremely low values of the absorption coefficient here in the subband gap region. So this low value is almost impossible to be measured with the spectrophotometer. Once we know the absorption coefficient at different temperature, we can calculate the radiative recombination coefficient B. The B values here at a certain temperature is just a function of the absorption coefficient, intrinsic carrier density, and refractive index. We can just substitute the values of alpha at different temperatures and wavelengths that we just published. Then we have the values for B at different temperatures here. So just from the luminescence spectra, reflectivity, and the thickness of the sample, we can establish two very fundamental parameters: the absorption coefficient and the radiative recombination coefficient. The first one represents how well a certain material can absorb light. The second one represents how well that material can emit light. Now we can extend the same principle to different materials. Here are the results for perovskite. For this type of perovskite, we know the thickness, reflectivity spectra, and the luminescence spectra. Then we publish the absorption coefficient of this perovskite material at different temperatures. Another application, when you work on new material, let's say like 10 different new materials, you can employ optical methods to predict the maximum open circuit voltage of the solar cell if fabricated from these materials. Even at the material stage, we don't need to make the complete device. And here we investigate the novel two-dimensional TMD materials. This figure just shows the optical microscope images of the exfoliated monolayers of 4 common TMD materials. We confirm the thickness of these materials with the AFM measurement, and then their quality with the Raman spectroscopy. So basically, we perform different ways to confirm that yes, they are the materials that we want to make. Then we measure the absorptivity and the luminescence from the monolayers. So this figure just like the sample for the molybdenum diselenide monolayers. So I just put here just as an example. And based on this quantity, we can calculate the implied VOC of the materials. This figure on the right-hand side just shows the predicted implied VOC of different TMD's monolayers and some of our perovskite film at the ANU. From this figure, the preliminary conclusion is, although the light absorption into the TMD's material is quite low, roughly just around 10 to 15% because it is too thin, some of them can potentially be a very high in light VOC. So this properties is promising for PV application, but of course, 2D TV is still in a very early stage for PV application. Now, let's move to some material-specific application. First, let's start with silicon. If we combine the imaging and spectroscopy mode, luminescence is a very powerful tool for multi-scale characterization of the defects and impurity inside the silicon solar cell. Let's see an example here. This is a typical luminescence spectrum from silicon with defects. This is the band-to-band emission of silicon, and this is a defect peak. If we don't use unabsorbed filters, the luminescent intensity image will contain the signal from both silicon and defect. It's not a true representative for the material quality. If we want to capture the normal BL intensity image, we have to use a short burst filter around 1300 nanometer. And if we want to capture the BL image from the effects, we have to use a long burst filter also around 1300 nanometer. This is an example of the intrinsic BL intensity image from silicon, and this is the defect image. You can see that they are complementary each other. And when we use an adjustable objective, we can keep zooming in more and more, and eventually we have the multi-scale imaging. And once we locate the region of interest, we continue using spectroscopy and mapping techniques to investigate the distribution of different defects and impurity with very high spatial resolution. This is a typical bare spectrum emitted from a dislocation cluster on silicon. And this part here is emitted from the dislocation core, and this part is emitted from the impurity and other defects decorating around the dislocation. So once we know which part of the spectrum is emitted from which defect and impurity, we can perform the very high resolution map for different defects and impurity. For example, here we perform the mapping here. So for location A, we have a very strong emission from the impurity, but low emission from the dislocation core. For location D, we have a strong emission from the dislocation core, but zero emission from the impurity. What does it mean? It means location B here is a clean dislocation, and location A is heavily contaminated with impurity. We confirm these findings with the micro XRF results here. So that's for silicon. Basically, that's for silicon wafer. But in a complete solar cell, there are many other layers, right? How can we characterize them? The basic idea is if we use an appropriate excitation wavelength, the excitation line will be absorbed by different layers, right? From the absorptivity of each material, we know which excitation wavelength we should use. And each layer has its own BL signature. But the problem is, at room temperature, because of thermal broadening and thermal quenching, the detected spectrum is usually very broad, and we cannot distinguish the signal from each layer. But at low temperature, the luminescent spectrum is very sharp, and very often we can distinguish the signal from each layer very clearly. So, and this phenomenon gives us a way to investigate the different layers inside the silicon solar cell. Here, a silicon substrate with a diffuse layer and silicon nitride passivation film on top. This is the total photoluminescent spectrum we get with the 532 nanometer excitation wavelength at 80 Kelvin, very low temperature. The P1 peak here, that's the emission peak of the silicon nitride film, and the intensity and energy level of this peak depends strongly on the composition and the thickness of the film. The P2 peak here, that's the band-to-band emission from the silicon substrate. And the P3 peak case, that's also the band-to-band emission, but from the diffuse layer. So it shifts to the longer wavelength compared to the P2 peak because of the band gap narrowing effects in heavily doped silicon. And the intensity and the energy level of this peak, of this P3 peak here, strongly depends on the doping profiles of the diffuse layer. So we utilize this P3 peak to develop a method to map the sheet resistances of different fingers in the IBC cell recursor. Here we can detect the broken fingers even in the micron scale here. And we utilize the P1 peak here to develop a method to image the thickness of the passivation film. So these are some of the applications from this graph here. And further, luminescence also offer many opportunities to understand and optimize the new passivating contacts for solar cell based on polysilicon film. At low temperature, the polysilicon film emits a characteristic peak at the energy lower than the crystallized silicon band gap, and this before halogenation. After a standard halogenation treatment, we can detect another peak between 800 and 900 nanometer, and this is the typical emission from halogenated amorphous silicon. Also, the polysilicon signal in RISC. What do they tell us? So it means the polysilicon film contains some amorphous phase, and hydrogen has been introduced into the film. Hydrogen does two things. First, it creates bonds with amorphous silicon phase inside the polysilicon film to create halogenated amorphous silicon. And second, it passivates some non-radiative effects inside the polysilicon film. And different halogenation technique here give us different responses. So this method gives us a very fast way to investigate the halogenation mechanism inside the polysilicon film. Now, we move to perovskite. The idea is once we understand how light is absorbed, emitted, and how light can be captured, we can develop a fast method to capture the optical bandgap images of perovskite solar cell. So, on the right-hand side here, the absorption process gives us the absorption spectrum in the red color here. The emission process gives us the emission spectrum in the blue color. And the peak of the emission spectrum is similar to the absorption ratio here. And this value represents the optical bandgap of the material. And from the imaging tool, we can capture an image of the peak energy of the luminescent signal of the materials. And based on that, we can extract the bandgap image of the perovskite solar cell. And this is an example. So this is the bandgap image of a perovskite solar cell from our lab. And we can also have the implied VOC and ideality imaging technique, ideality vector imaging technique for perovskite solar cell. So basically, from the BL intensity, we can calculate the implied open circuit voltage. Then we vary the illumination intensity. We can convert each BL intensity into one values of implied VOC. Then we fit the implied VOCs versus the illumination intensity curve here. Then we have the ideality vector of the solar cell. In the imaging mode, we have the image of implied VOC and ideality vectors, not just a single value. And these are examples of the implied VOC image and ideality vector image from a working perovskite solar cell. Then we can move one step further if we don't change the illumination intensity, but we change the temperature. At each temperature, we can convert the BL signal into implied VOC. And we fit the implied VOC versus the temperature curve here, we can have the activation energy of recombination. And in the imaging mode, we have the image of the activation energy. So these are some applications of the imaging technique on perovskite solar cell. And another method that we can develop is spectrally and spatially resolved absorptivity Rabier spectra. Again, this formula just describes the relationship between the luminescence spectrum and the absorptivity spectrum of a semiconductor. And in this formula A here, that's the absorptivity. So it means that from the Bayer spectrum, we can extract the absorptivity spectrum. And in this graph here, the red curve is an example of the Bayer spectrum captured from a perovskite solar cell. The blue curve is the absorptivity spectrum that we extracted from the Bayer spectrum from this formula. And the blue dashed curve here, that's also the absorptivity spectrum that we measure using the spectrophotometer. You can see that for the wavelength beyond the optical band gap of the materials, the absorptivity is supposed to be really small, but the values from the spectrophotometer methods are saturated around 10% due to the parasitic absorption in other layers of the solar cell. So even if there were no parasitic absorption, it would be extremely challenging to measure the very small absorptivity at the short band gap wavelength using the spectrophotometer. The absorptivity extracted from the Bayer spectrum is not affected by the parasitic absorption. And also you can see here, the BL intensity is still several order of magnitude higher than the noise spectra in the short band gap region. Because of that, the BL-based absorptivity value should have a high signal-to-noise ratio even beyond the optical band gap. And using this luminescence-based absorptivity method, we can have several applications. Here, a perovskite solar cell will left in the air and monitor it for a few days. At the short band gap wavelength region, the absorptivity is very sensitive to the degradation. So in particular, at the early stage of degradation. So here you can see very clearly that the edge is degraded with time because the air slowly invades into the cell edge. And also these spots that I put the circle here, they are due to the pinhole through the gold layer. And another application is that we can separate the absorptivity of the perovskite and silicon cell in the monolithic perovskite silicon tandem solar cell. For the tandem cell, the question is whether the relationship between the BL and the absorptivity is still valid for the top cell. To answer this question, we need to take a step back. I just repeat this phenomenon again because it's quite important. Under excitation, each Coulomb element of the material will generate photons, and these photons move toward the surface. On the way moving to the surface, they are reabsorbed, and at the surface, some of them are reflected back. Some of them can escape out of the sample. So to get the final photon flux emitted outside the sample, we have to integrate this emission for the entire thickness of the sample and account for the reabsorption, which is related to the absorption coefficient, and account for the reflectivities at the front and the back. And because of this phenomenon, in this formula, the absorptivity here contains what? It contains the thickness, the reabsorption, and the reflectivities at both sides of the samples. When we have a bottom, the bottom silicon cell, whether this relationship is still valid or not. So the answer is yes, it's still valid. This is because the emission from perovskite just between 650 and 900 nanometer. At the longest wavelength, 900 nanometer, the absorption depth in silicon is just around 30 micrometer, and the silicon cell usually around between 100 to 150 micron thick. So the BL ray from the top cell cannot pass through the bottom silicon cell and then being reflected back from the rear side. In this case, only the reflectivity at the front of the tendon cell and at the interface between the poroscan silicon are important, and we can treat the reflectivity at the silicon and poroscan boundary here in a similar way to the real reflectivity of the single junction poroscan cell. So this relationship is still valid. Because it's still valid, we can apply that relationship to extract the obstructivity spectrum from the Bayer spectrum from silicon top cell, from the poroscan top cell. The left figure here show the Bayer spectrum, the obstructivity spectrum extracted from the Bayer spectrum, and the total obstructivity spectrum measured by the spectrophotometer. And these are in logarithmic scale on the left-hand side. And the figure on the right, again, the red curve is the obstructivity from the poroscan layer extracted from the Bayer spectrum. The blue curve is the total obstructivity of the tendon structure that we measure using the spectrophotometer. And the black curve is just the difference between the two curves. So this is the remaining obstructivity of all the layers, including the bottom silicon cell. And we can see that around the optical band gap of the poroscan material, around 790 nanometer, the obstructivity of the poroscan layers is just probably around 40 to 50%. And there is still a significant fraction of the light obstruct in the bottom cell. When we combine the BL-based and spectrophotometer-based method, we can separate the obstruction inside the poroscan film from the entire tendon structure around the poroscan optical band gap. So this is almost impossible with the conventional spectrophotometer method alone. And also now, we have BL intensity, we have optical band gap, we have short band gap obstructivity in the poroscan shopper. So basically, we can have the same derivation study of the tendon cell as what we did for single junction cell. So in conclusion, the key message from my lecture today is, yes, light-matter interaction in BV material is very complex. But when we know the science and of the optical phenomenon inside our materials, where the lights are shot, where electrons and holes move, and how they recombine, and how light is emitted and captured, these complexities impact the opportunity to explore many different applications. For example, we can extract many different fundamental parameters for silicon, poroscan, and 2D materials. We can investigate the distribution of different effects and impurity in the absorber, or we can probe different layers in our solid cell. And the nice thing about optical spectroscopy is that once we're successful with one material, we can try to extend the technique to other material. And my research are supported by this organization, and these are my collaborators. And a final note, so I have to clarify here. Most of the applications presented in this lecture were selected from my team result as an example. In the literature, there are many more applications of optical spectroscopy and imaging, and some of optical phenomena are much more complex than the simplified principle that I presented in this lecture, just to be clear. And that's it for my lecture today. Thank you very much for your attention.
Brilliant. Brilliant. Thank you very much, Yu. Again, a wonderful talk and very comprehensive on different types of spectroscopy techniques and how we can utilize that in measurement of cell performance. So to the audience, again, please put your questions through the Q&A. So just submit them through that and I will get through as many as I can. Just to kick off, Hugh, so when you, I think you mentioned right at the beginning about the optical setup and references. Just a quick question on the types of reference materials that you might want to choose when you're measuring different types of surfaces. Do you have any advice on that? Because I know a lot of students often come across that challenge of picking the right reference materials when they're doing either any of these sort of optical characterization?
Yeah, I think usually like I think I think the best reference sample is gonna be the Spectralog. That's the Lambert reflector, like that we can easily buy it from any like optical supplier. So that's gonna be our golden sample that we use to do the calibration for most of the measurement that we do, from the reflectivity measurement, transmissivity measurement, and even the calibration for the luminescence.
Brilliant. And in terms of the you know, you've got a lot of different optical characterization techniques here, and where you're looking at, like in the slide, defects, stacks, even the fundamentals. What future do you see for these sorts of contactless characterization techniques in industry as an alternative to doing IV measurements to get all of that data? Can this actually replace in future contact IV measurements, for example, to extract a lot of the information?
I think I would say it will support the IV measurement rather than completely replace the IV measurement, because IV measurement is still the final result that you ultimately want to get. And for the optical measurement, usually it's sum up the phenomenon that we omit from the optical measurement. Yeah, that usually don't present in the optical measurement, but usually we observe it in the real IV measurement. For example, if you from the optical measurement in Risible, you can reestablish the pseudo IV curve, the current voltage curve, but that current voltage curve won't be accounted for series resistance loss.
Yeah,
but
so there's a lot of, I guess, image training you could do to extract a lot of that information, but there's still a long way to go. There's a question on here: is it possible to determine defect position by any optical measurement?
Yes, I think not only optical measurement, but I think like for other electrical measurement, we also able to determine some of the energy level of some of the defects. For example, you can use DLTF, deep level transient spectroscopy, to determine the energy level, or you can use the photoluminescence spectroscopy to determine that also, because like if it emits the luminescent signal and each defect at the specific energy level, they will emit a characteristic peak, and based on the peak position, the energy of the peak, then we can like extract the information about the energy level inside the band gap. But again, it's not a universal technique. So depending on what type of effect that you are looking at, maybe we need the combination of different types of technique to correctly determine the energy level of the particular defect.
Brilliant, thank you. A question from a fellow panelist: how does metastability affect specific spectroscopy measurements? For example, PL spectroscopy for perovskite samples.
So the metastability, yes, that's one of our biggest challenge when we do the measurement of perovskite. So I think the way that we work around that problem is that usually we do some like reconditioning first. Let's say we illuminate our perovskite material for 5 minutes under full one-shot illumination, and then we just observe the luminescent spectrum and until it stabilizes there. Then we do the characterization. Or if we have the fully working cell, we can apply the voltage and then we observe the current, and then up to a certain point where the currents like stabilize, then at that point we do the characterization. Yeah, so that's the biggest challenge when we work on perovskite solar cell.
Brilliant, thank you. Again, another question from the audience. Hello, thank you for your talk. in the part regarding the assignment of the different single peaks making up a total spectrum, how can you be sure that the individual peaks are exactly from this peak? Are there any sub-processes which can lead to peak shifts, peak broadenings that may mask serious changes in a sample?
Yeah, I think because in order to confirm which peak from which material, we do the measurement for individual material first before we confirm it. So let's see here. We have different peak from different layers, right? But in order to determine that, we do the measurement just on a single material first. And after we deposit 3 of them, we got like 3 similar peaks from individual materials. So that's how we can confirm that the 3 peaks are from the 3 different materials. And yet, when you deposit material on top of each other, somehow the peak here, the energy level can change a little bit. Yeah, in some cases it can change quite significantly because you have interaction between the 2 materials together. But at least from the result from each single materials, we can quite confident that yes, that is the peak from that material we are looking at. So if the first time if we do the measurement, we get the 3 peak, and for sure we won't know which peak is from which material. So the only way we work backward.
Brilliant, thank you. Further to that, and actually it's a question that I was also going to ask in the broader sense, but specific to this, is machine learning able to improve the detection of singular peaks in a total spectrum? And then my follow-on question to that one from the audience is actually, in your different techniques here, where do you see ML coming into this space and future works for a lot of the students that are present in the audience about where they can take this research forward?
Yeah, I think machine learning is a very exciting area. I think if we can incorporate machine learning into this type of like spectroscopy technique, that would be fantastic. Yeah, so it can save us a lot of time. Yeah, but before we are able to apply the machine learning, we need to have the large enough database first, right? Let's see, we have like hundreds of thousands of different materials and at different conditions, and then we capture the spectrum and then we store in the database. And because the machine learning at the end is just like a tool to learn quickly what's happening with the data set, right? So yeah, and we use a machine learning quite a lot to do the characterization for industrial cell, where we have the IV curve, the BL intensity image, because we have a very large data set. But this type of spectroscopy technique, when we do the measurement, we have 5-10 single spectrum. So it's a little bit challenging to get like thousands of spectrum. But if in the future with the advance of the technology, if we have a way to capture like different types of spectrum for a reasonable amount of time, then we can build a large enough data set where we can apply the machine learning.
Brilliant. Yeah, as is the case, always generating that large data sets is always a big barrier. Another question from the audience: why 532 nanometer is chosen as the exciting wavelength?
Yeah, because in our lab we have 532. Yeah, that's, of course you can use other excitation wavelength like 600 or 450. Yeah, it will give you the same information, but because like a different wavelength, the amount of excitation line will be absorbed by different layers will be different. So in stack up, you have B1 here, maybe you have B1 a little bit lower, B2 a little bit higher. So the relative spectrum will change, but the peak position, it should be the same.
Brilliant. Just before we finish, I want to ask a question about errors in these measurements and what are some of the steps you take to minimize errors, particularly for the, again, for the early career researchers who are just starting out in these sorts of measurement techniques. We often get, okay, how can I improve my process? Do you have any advice on some of the sort of the common errors that you come across and how you tackle that?
Yes, I think the biggest error that we often face is we we didn't account for the spectral response of the system. That's one of the error that I often see is like most of the new PhD students or early career researchers when they work on this spectroscopy technique, because like what you detect from the detector is already distorted by different things, like the filters has the responses, and the objective lens also has a response, and even the camera is have the quantum efficiency at different wavelengths. So my advice is when we work in this field, the two things that you need to have. The first, you need to buy the calibration light source. So because from that light source, you will know what is the expected spectrum from that light source, and then you just use your tool to detect that light source. So from the spectrum that you detected, and from the standard spectrum that you should receive, then you can establish the correction factors there. So that's the one thing that we need to have, always need to have when we work in this field. And the second thing is the standardized sample, which is the spectrum. We can buy it. So that's going to be useful to do the calibration for the reflection, transmission, and even sometimes for the emission measurement.
Brilliant. Thank you very much, Hugh. That was a wonderful talk, and thank you for going through those Q&A. Again, there are questions over in the Q&A if you'd like to if you have some time to answer through them. We very much look forward to welcoming you in the UK in June, Hugh. So for the audience as well, if you want to network, please do get in touch with Hugh. He'll be visiting us and hopefully coming to PBSat as well. Thanks, Hugh.
Right. Thank you, Tas.
I'd like to introduce our next speaker now, Dr. Katie Shanks. Katie, are you able to share your screen?
Yeah, can you see that all right?
Yeah, if you just go full screen. So yeah, it's Dr. Katie Shanks from University of Exeter, and she'll be taking us through optics for photovoltaics. Brilliant. Over to you.
Great, thanks. Yeah, so this will be looking a little bit more at how you can manage or condition the incoming light before it hits your device. And that we'll be looking a little bit at solar concentrators, so optics, which concentrate light onto the solar cell, and also different other tricks that you can use to manage the light so it's optimized for your device instead of optimizing your device for the light. So yeah, there's three key things we'll be looking at. There'll be solar concentrators. So mostly these get used to increase the energy input into your system. And if you increase the energy input, you can increase the energy output. There's also optics used that do spectrum filtering or spectrum splitting. So it's good we had that talk just there to kind of explain it a little bit about the spectrums you can have. And this can also lead to higher cell efficiencies or higher system efficiencies if you're splitting the wavelengths to be used in, for example, PV and solar thermal technologies, or for example, in building integrated systems where some of the light is going to the inside of the room and being used for lighting, or also earlier mentioned was greenhouses. So you can use the incoming light more efficiently if you use some optics to split or filter it. And then you can also use anti-reflective coatings or layers to help increase, again, the amount of sunlight getting to your device, but it also increases the performance throughout the day. So if you've got a solar panel or a low concentration system that's static, so building integrated, for example, then obviously when the sun's low in the sky or at wide angles, there can be a lot of reflectance loss. So we can have anti-reflection coatings in optics. And also sometimes these coatings or optics can improve the weatherability or the durability of the system. And then last but not least is the aesthetics. So there are options for optics that could increase the aesthetics. And that's not really been looked into too much, but there's a little bit of it in terms of, for example, the dye-sensitized solar cells and other optics. You can also get dye-sensitized solar concentrators, and we'll talk about them as well. So first of all, one of the reasons why we do solar concentrators is because of this increase in solar cell efficiency. So I'm sure you've all kind of seen this graph plenty of times, but some of the highest efficiencies are under concentration. So that 47.6% record efficiency up at the top there is under 665 times concentration. And of course, a multi-junction solar cell as well. But yeah, if you want to get to very high efficiencies, then concentration is quite a good way to jump up quite a lot, actually, depending on your solar cell. And this is quite an old graph now, but the limits haven't changed. So when you're talking about the theory behind it, you have this absolute kind of upper limit due to the thermodynamic limit. And this is if you had an infinite number of junctions and you were able to increase the sunlight, concentrate the sunlight by 46,000 times, then you could have an efficiency up at 90%, which we'll never get to that. But it's good to know that there's a lot of room to maneuver in if you do have concentration and you've got multi-junction solar cells. And then obviously, if you've got just one single junction, and the efficiency limit is of course 33.3%. But if you put concentration onto a single junction solar cell, you can also bump up a little bit, with the theoretical limit being 45%. But yes, that's just to give you an idea of how concentration can increase those efficiency limits. So for those of you that don't really know much about solar concentrators, very basic idea shown from the figure on the left. So if you have your solar cell, and it can be a single cell or it can be a panel, and you've got a mirror or a lens, then you can increase the sunlight incident on that device. And if you're increasing the energy into it, then you can increase the energy out of it. Obviously, that gets a bit more complicated when you think about temperature, performance, resistive losses, for example. But there are ways around that as well. Yes, and some of the other advantages around using optics to increase that energy harvesting, instead of just increasing the amount of PV panel or PV material you have, is, for example, cost, depending on the PV material you're using. So, for example, multi-junction solar cells can be very expensive. So quite often we can have a multi-junction solar cell, small area, and then you have your optics that actually gather all the light and focus it to your small solar cell, and that way it kind of reduces the overall cost of the system. And then there are other things that are starting to emerge, like carbon footprint. So the optics, depending on what they are, might have a lower carbon footprint than the solar cell material. So solar concentrators, there's lots and lots of designs. So that this is just showing lots of pictures of the possibilities. So in the bottom left is a very basic VTRIF concentrator. They get names that follow their geometries. In the middle, there's a kind of a linear Fresnel reflector. So it's lights hitting these flat mirrors. They're all at different angles, and they're all reflecting to the top receiver, which for a linear system is typically used for solar thermal, but can also be used for photovoltaics. You have a basic lens system. So for example, the image on the right is a Fresnel lens focusing light to a solar cell. And the image on the left there in the middle and at the top left is a Cassegrain. So similar to what gets done in telescopes. And I think, yeah, this is a better image of a Cassegrain. So similar to a telescope, light comes in, hits a primary dish, primary reflector, which focuses to a secondary reflector, and then it focuses down to either a solar cell or another type of optic. One of the reasons I'm showing this one is because you might see that it's quite complex. So you've got 1, 2, 3 optics there, 3 stages, which isn't good. So that would mean there'd be a lot of losses. Even though you're increasing the amount of light that's maybe getting to your little high efficiency solar cell, each stage you'll have some optical losses. So it's one of the considerations. And then Fresnel lenses are basically truncated lenses. So on the right, there's how they get truncated down so that curvature is maintained, but the bulk, the thickness of the material is reduced. And that gets done to reduce the absorption. And then you only have some reflective losses and a small amount of absorption still taking place. And so the Fresnel lens and the Cassegrain are kind of the 2 main or most popular concentrator systems. There's also the compound parabolic concentrator, which I'll show later, and that's a low concentration device. So some of the terminology I've been using, which splits up these different categories of concentrators or optics. For photovoltaics, you have concentration ratio. So it can be low, medium, high, or even ultra high. Now we've got, and those are the definitions there. The term suns gets used, which just means how much you're multiplying that sunlight by. The geometry, obviously you can have parabolic, hyperbolic, dish, trough, 1 stage, 2 stage. Tracking methods. So if it's a small optic, low concentrating system, then you don't typically need any tracking. It can be stationary, and these are often used in building integrated systems. One example on the left there is a luminescent solar concentrator. So these devices have a luminescent material, and there's also a picture, kind of the third picture in. I don't know if I can get my, what do you call it, the little device, but it's a third picture in that has the luminescent solar concentrators where light gets absorbed by the material, the bulk material, and then it gets re-emitted to the edges, as you can see in that picture. And that's where you'd have solar cells. So you can have colored windows, for example, with some light going to the solar cells. And that's one example of a kind of stationary building integrated optic. It's very suited to building integration. And then you have, as you increase the concentration ratio, so increase the size of your optics or reduce the size of your solar cells, you need higher accuracy tracking. So you need 2D, 3D tracking methods. And as I mentioned before, the main kind of mainstream optics are Cassegrain or Fresnel lens, but you also have these smaller optics, which sometimes get used as secondary optics, and these have names like homogenizer or CPC, the very popular one, or also light funnel is a terminology that gets used. This is just giving you a really broad kind of scope of what solar concentrators are and what they can look like, or their range of designs, which is quite a lot. As I mentioned already, concentration ratio is how many times you're increasing the sunlight by. So it can be, the unit can be suns, it can also just be X times. So on the right hand side there is a simple diagram of a Fresnel lens that's 500 centimeters squared in area, and then it's focusing to a solar cell which is 1 centimeter squared. So you would say that's 500 times. But importantly, if you are reading articles about solar concentrators, is to be aware of what they're talking about. So there's a few different definitions, a few different variables. So there's the geometric concentration ratio, which is the one that gets used mostly when describing a system. And that's simply the area of the Fresnel lens, or the area of the primary optic divided by the area of the receiver, the area of the solar cell. So for example, in that top right, we've got a geometric concentration ratio of 500x. But depending how many losses are in a system, that could, the actual effective concentration ratio, which is the little equation is down the bottom there, it could be a lot lower. And this is due to the and you've also got the optical concentration ratio. So the optical concentration ratio takes into all the optical losses, takes into account all the optical losses. So for example, Fresnel lens will have some reflection when light's going into the lens, and we'll have some absorption, and we'll have some light scattered when it comes out of the lens. And maybe not all the light will be hitting the solar cell, for example. And so all these losses, you take them into account, and you have your optical concentration ratio, which is more realistic. So the geometric concentration ratio kind of acts as a maximum, and the optical concentration ratio is a little bit more realistic. It gives you kind of your maximum, but taking into account your materials that you have available to you, and the quality of the optics that you have available to you. The effective concentration ratio is actually, you can calculate it based on these numbers before, the cell efficiency, the optical efficiency, and the geometric concentration ratio. But you can also measure it, measure your IV curve of your solar cell under this concentration, and you divide it by, you divide that result by what the solar cell was giving out at when there was no lens. So when there was no concentration, that can give you an idea of what the effective concentration ratio is. They've all got kind of their inaccuracies with each one, depending on how you use it. And quite often people will go back and forth between these terminology in a paper if they've done some simulation and some experimental. They'll kind of validate all the values that they've said they've got. And of course you can have optical efficiency and module efficiency, which is those equations on the right. Now, in terms of optics theory and optical losses, there's a few key things. They don't change very much. There's always refraction, there's reflection, whether it's total internal reflection or from a reflective surface. There's scattering, so the image there on the right of a water surface, which always be aware of the fact that optics or any material is never going to be perfectly smooth. So there's always going to be some, at least small amount of scattering happening. There's kind of divergence and, the separation of the wavelengths, which can be good if you're wanting to do that in terms of spectral splitting, but it might also lead to losses in a specific wavelength on your solar cell, depending on what your setup is. And then, as I mentioned before, there's optical quality. So in this kind of bottom image, we've got your little cell, and then it's actually looking down into an optic. Depending on the optical quality, it could be hazy, it could be a rough surface, it could be bubbles if you've made it yourself. And these would increase the optical losses significantly, so you don't actually have very much light getting to your solar cell, which is important. So if you're adding in optics to try to increase the energy incident on your solar cell, if all the optical losses add up so that you're not actually gaining much, then you can see how that wouldn't be worthwhile. And then there's also the geometry of the system. So an optical design needs to have geometry that has a tolerance to it and takes into account the refractive indices of all the materials and how the light's going to hit the solar cell and how it's going to perform as the sun moves across the sky as well for a stationary system. So a little bit more detail on optical losses. So as I said, you can only really have three things happening when a light hits a surface or material. So you've got transmittance, reflectance, and absorption. And these will add up to 100%, so the light can't be doing anything else. And quite often in some articles, they will take out one of these values. They'll say that absorbance is negligible, for example, or reflectance is negligible. And then they'll say that, the other two are the things that add up to 100%, and that makes their calculations a bit easier. But there is always three things there. And on the left-hand side is a figure of how all these things I've been describing will be happening at every interface. Okay, so as soon as light hits a lens or hits your solar cell, for example, you're going to have some light being scattered back, reflected, and it will be reflected predominantly in one direction if it's a smooth surface. As I said before, there's no ideal surface, so there will always be some scattered reflectance. And then, of course, if it's a refractive material, a lens or transparent material, then some light gets refracted. And then on the exit surface, you'd have the same situation. You have the specular transmittance, so most of the energy is going in one direction, following Snell's law. But there will also be a lot of scattering because of the surface, depending on the roughness of the surface. And there are models that estimate this kind of distribution. So here it's showing the kind of bidirectional reflectance and transmittance distribution functions. There are other ways of estimating or modeling where the light goes when it hits the surface based on its surface structure. And things like surface roughness, for example, might be used depending on what simulation software. If you're using a simulation software, it will use different methods of calculating that. And you can use this for solar concentrators for all the optics, or simply just for your cover glass and your encapsulant. So I know that in terms of device research and the material choice, you might be trying to get a solar cell efficiency to increase by 1%, which is significant in the world of solar cell research. But then as soon as your cover glass and your encapsulant on top of it, something to seal it and protect it, you're probably going to lose somewhere between 5 and 10% straight away. So it does make a difference if you can optimize those things, so you're not losing out on that readily available sunlight. And this image is a little bit bloody. I think I made it too big, but this is just explaining in kind of a easier, understandable way where the light goes. So this is a CPC system on the left, compound parabolic concentrator. But of course it's got cover glass, it's got some encapsulant, some kind of optical adhesive to optically match everything. And then it's connected again to a solar cell, which is connected onto glass. And so each interface where the refractive index changes, you're going to have some reflectance, you're going to get some absorption through each material. The CPC is designed such that total internal reflectance is meant to happen at the corners, at the surface. But if that surface isn't completely smooth, then there will be some light loss there. And depending on the angles and where the sun is, you'll also get some failed TIR and whenever you're beyond the acceptance angle. And similarly, this would happen for a Fresnel lens or a Cassegrain optic or any type of device. And this is all following Snell's law, and it just depends on how smooth that surface is. So again, we've got surface roughness, and this image on the right is an example of a poorly made optic. It's a kind of a light funnel. So in the top right there is what it looks like, the geometry on a side-on view. And then the images are kind of looking down into the optic with the solar cell at the bottom. So the idea is that light gets focused onto this optic and then is totally internally reflected towards the solar cell. Now, if the optic is hazy and has bubbles, etc., then you're going to have a lot of light loss. You can kind of see from these first two images with the kind of bright light on them, they're a lot clearer, a lot better made. And one way of knowing if an optic is performing well is if you can see the solar cell many, many times. Okay, so that's what they're meant to be doing. They're either, you can think of solar concentrators or optics for photovoltaics in two ways. You can think of them multiplying the number of suns, or they're effectively multiplying the number of solar cells that the sun sees. So when we're looking down into these optics, the more solar cell you can see, the more concentration is happening, or happening effectively. So these are all just obviously focusing to only 1 centimeter, one solar cell of 1 centimeter size, 1 centimeter squared size, but we're getting a concentration of, well, I'm not going to count them, but higher. And you can see if you compare the middle one, so the middle one actually has this kind of outer reflective film, as well as the refractive optic. And that means that any light that doesn't get totally internally reflected will still get captured. If you look at the top right diagram, it kind of shows there the little dashed arrows. Due to the surface roughness of the optic, if any light is, or because of the angles, if there's too many reflections, any light that escapes the refractive optic gets captured by the reflective film. And you can kind of see it working from looking at these images, because if you look at the far right of, so if you look at the middle image and you look at the far right of the middle image, you can see 3 solar cells, or the start of 3 solar cells. If you compare that with the image on the left, on the far right, you can actually only see 1.5 of the solar cells there. So that's just a way of visually inspecting if an optic is working. Now, in terms of how high can you take solar concentrators, I think I mentioned before about the 46,000 absolute limit. And this is because of the sun divergence angle. So if people remember back in high school, you get taught that, or at least in optics, you get taught that the light from the sun is parallel, but that's not the case. So it's got this very small divergence angle of 0.27, which actually messes up a lot of things when you're trying to concentrate the light. So because of the size of the sun, this is how you have this 0.27 angle, because light can come from one side of the sun or from the other side of the sun. And so any point on your material or your optic or your solar cell, it will have this minimum and maximum incidence angle, even though it's direct from the sun. And then obviously if you've got different stages, so different interfaces and optics that the light's passing through, this small angle will get bigger and bigger, because we're adding kind of more uncertainty at each interface. So this image here kind of tries to show that uncertainty compounding to the point where you can get light missing a solar cell, for example, or you might require much higher tolerances in the optical alignment. So a summary of solar concentrators before I move on to the other topics. They can increase energy input and hence energy output and energy efficiency limits, which are all good. But having high quality optics is difficult, or can be difficult and can be expensive, to a point where you could argue there's not any point in having a very expensive, very high performing optical system if you could actually just have cheaper solar cells instead and get your same power output. So that's definitely always a consideration. Make sure you're choosing setup that makes the most sense for your application, depending on the limits of your location, for example. High concentrator systems, so whenever we go to more than 100 times or 100x, we'll definitely need cooling and tracking systems. And those could be simple, so you can have passive cooling. It doesn't need to be active cooling, which is water-based or pushed air. So there are passive cooling mounts that have been designed where they're just carefully designed fins, for example, and tracking or low tolerance systems for misalignment become more important. I'll talk about beam steering in a little while, which kind of helps reduce that need for tracking or high tolerance systems and high accuracy systems. And low concentrator systems are gaining more and more interest because they can be used for building integrated, because they don't need tracking systems, they don't need cooling systems. They're relatively inexpensive to make because they're quite small optics. And so there's quite a bit of research into low concentrator systems for building integrated technologies. And actually low concentrator systems also you can use with single junction solar cells. So you could take your silicon, you could take perovskites or CadTel, and you could do a small amount of concentration and see if your efficiency goes up a little bit. And that hasn't yet been done for perovskites, or there has been actually a little bit done, and it's definitely been done for silicon. And I'm not sure about the other solar cells, but it's definitely worth a try. And this is just a figure kind of describing some of the technology breakthroughs in terms of optics for PV. So, I mean, they've been around. The method of concentrating light has been around for a while. So lighthouses used to have giant parabolic mirrors, actually, that helped kind of spread the light out to ships at sea. And then at some point, they discovered PMMA material, which was a lot lighter. But that didn't PMMA lenses weren't used until they discovered also Fresnel lenses, or sorry, other way around. They had Fresnel lenses, but which were a better lens, a lighter lens. But then when they found PMMA and combined those two things, they then started using that for everything. So PMMA Fresnel lenses actually kickstarted a lot of research into solar concentrators. And now in lighthouses, you have PMMA Fresnel lenses instead of the parabolic mirrors. And then you've got CBCs, low concentration optics. You have up here near this concentration limit I was talking about. That depends on how many materials you're using for your optics and what the refractive index is of them, and also a little bit about segmented reflectors. And if you can play around with that curvature and breaking up the curves that you're using that concentrate the light. But yeah, so this is kind of giving an overview of that. Now, if we move on to spectrum splitting and spectrum filtering, the main idea behind this is that you can increase the efficiency of your system overall, or you can increase how efficiently you're using that sunlight. So obviously, if you've got a single junction solar cell, it'll be absorbing a certain range and it'll be limited to less than 30% of the spectrum. If you're using some of the light to also light a room or go to thermal energy, then you're effectively increasing the efficiency of that system overall. And as I said before, the luminescent solar concentrators are quite well adapted to this sort of technology. CadTel, there's also been some research into cadmium telluride and thin film technologies for this. It depends on the application completely, what your goal is and what combination of technologies you want to use. Optics or solar concentrators can be used to, instead of having semi-transparent solar cells, you could have solid solar cells, but then they're spaced out with optics, for example. And in terms of, there's also a lot of research into combining this with things like phase change material, or materials that produce electricity and change the thermal conductivity, which is advantageous if you're trying to cool or heat, or cool or insulate a building. So there's quite a lot of research still to be done in this field. There's definitely not been all the combinations of technologies yet. And it's definitely gaining interest because it's leading towards our net zero building targets. And one aspect of this, which I'll talk about in a little bit later, is if we're moving towards net zero buildings and hence needing more PV all over these buildings, whether they're just standard solar panels or they've got optics in them, they will probably not be at the optimum orientation. So we do a lot of tests under our standardized conditions of 1000 watts per meter squared, with light directly normal onto our solar cells. But depending on where they're put on a roof or on a wall, for example, they may not actually have that condition at any point throughout the year. So especially for vertical integration. So we did some research in the past looking at solar windows, and specifically for cities and areas where you've got a lot of skyscraper buildings, where space is an issue. And one of the things that came up there was, okay, if you've got something vertically installed, then that's probably one of the poorest positions, okay, in terms of gaining energy throughout the year. And yeah, there's no point, if it's facing south, it's not going to get any direct sunlight head on at any point. It's always going to have this angle of sunlight, which is going to be at least 15 degrees or more. So that's a consideration, and I don't know if there's been much research into if you can optimize your anti-reflective coatings for that range of angles instead of the normal incidence, which is what we do right now. So these are definitely considerations that I think are coming up more and more when we're talking about practical installation, practical use. And yeah, spectrum filtering and splitting. We've talked a little bit, I think in the first presentation, there was talk about what the spectrum is indoors. There's also a lot of research into how the spectrum varies depending on your location and orientation. So the spectrum will change depending on how high the sun is in the sky. It'll also change depending on things like pollution, dust, water vapor, and obviously cloud cover. And you can have optics which are designed more for those spectra, or can manage that spectra so that it fits better with however your solar cell performs. If your solar cell performs best under certain conditions, you can definitely have optics that filter and split the wavelengths, or reduce a certain wavelength and increase another one if that's what works best for your solar cell to get those high efficiencies. And luckily, there is this resource called PV Lighthouse website, which can tell you what your spectrum is based on the module tilt and azimuth and longitude and latitude. And it can tell you the direct, diffuse, global, etc. So that's very useful depending on exactly what you're trying to do. And I think you can also change some of the kind of atmospheric inputs as well, which is useful. In terms of spectra efficiencies, just be aware whenever you are looking at your single junction or multi-junction systems, or if you are looking at optics as well. If you are working through from the start to the finish in terms of efficiency of light getting to your solar cell, what wavelengths that is specifically, how that matches up with each junction, just be aware of what wavelength range you're looking at, which will, if you do it right, it'll all calculate through to be the efficiency of the solar cell that we quote. But just be aware of, depending on what range you're looking at, you'll get different efficiency numbers. So always make sure you're looking at the full range. And this is just some examples of how you would calculate that through from the start of, your light hitting your solar cell, the external quantum efficiency, for example, and how that all adds up to give you your final overall efficiency of your solar cell or your system. So I've talked about optics that do spectrum filtering or splitting. But what, and you can either do that because of a material, or you can do it with a structure. So these are nanostructured ITO layers. And this is from a paper I did with people at UNSW, so here in Australia. And it was looking actually at thermal technology, so solar thermal. And the idea was, can you structure or pattern ITO on glass such that it lets in sunlight, but then reflects the longer wavelengths, the thermal energy at the longer wavelengths that gets kind of created in the receiver. So these are just some of the kind of structures we used, and depending on your nanostructure, or depending on the pattern, which is sub-wavelength, depending on that scale, it'll affect different wavelengths. So obviously you can have a structure which is big enough that it is seen by some wavelengths and not seen by other wavelengths, and that means it'll interact differently with those different wavelengths. And it can be pretty tricky to get right. And even if you simulate it and design it perfectly, obviously manufacturing these structures can be very difficult as well. But there's quite a lot of potential in this field for what you can do with those different scaled nanostructures. And that's kind of being seen in other topics. So there's the field of metamaterials, which is looking at this sort of stuff amongst many other things, where they're changing the pattern or the structure to what's the word, impact or change the signals, incoming electromagnetic signals, and it gets used for optics and photonics, as well as all sorts of signaling and remote sensing technologies. Now that leads us on to anti-reflection coatings. So anti-reflection coatings can be done by either matching the refractive index layers. So you're going from a nice kind of steady refractive index of air, which is 1, and then you're going slowly increasing up to the refractive index of your material, your PV device, to avoid this reflectance that we have at each interface. So the reflectance happens because of the change in refractive index. And one of the ways you can do that, instead of having lots of layers of material, which is quite difficult to do, lots of different layers, you can have your nanostructure to do that kind of graded refractive index instead. So this was an example of biomimicry that was done for solar cells. So back in the day, they looked at moth eyes, which have a very low reflectance. And the moth eyes have a low reflectance because it's advantageous for them to be camouflaged and not have reflective eyes to predators, as well as obviously taking in as much light. And this is an SEM image to the right of what their structure typically looks like on the surface of their eye. And this was copied to increase the amount of light getting into the solar cell, hence being anti-reflective. And since then, there's been lots of different variations of this design of these anti-reflective structures or coatings or layers. And quite often they get used for solar cells. There's also, I've seen some papers that talk about simply reducing the reflectance in laptop screens and mobile phones, but they can have a significant impact and increase on, as I said, the energy that gets to your solar cell. And these are just some examples here. And it's all about changing this kind of step to be more of a gradual curve. So in the image on the bottom there, you want to have as gradual a change in refractive index as possible. And so the idea behind structures is that because an incoming wavelength can't see such small features, if they're small enough, then instead it only sees a mixture of the two refractive indexes, and that gradually increases. So another way of thinking about it is about the porosity of the surface. So you've got air, you've got your material, and somewhere in between, the air starts to decrease and the material starts to increase. And that's how these structures typically work. Now you've got anti-reflective coatings from moth eyes. You've also got anti-reflectance wings, or very high transmittance wings, like the glass wing Greta Otto, which is on the right. And this has a much more complicated structure, a lot messier, I would say. It's got these little triangular shaped structures, which are less than 500 nanometers, only about 100 nanometers in width. And their heights, if you can see in this right-hand side of the slide, their heights change. And because of that slight randomness, or it's not completely it's not perfectly uniform, it actually helps this butterfly have very low reflectance, even at very wide angles of incidence. So when the sun is low in the sky, for example, this type of structure would help increase light getting into a solar cell. And on the left-hand side, we have the cabbage white butterfly, which has the opposite, has reflective wings, reflective white wings, which we're also looking into for very lightweight reflective materials. And you can think that if you have these types of biomimicry inspired structures, that you could make quite a compact solar concentrator that was just these thin coatings of materials, and doing your reflectance and your anti-reflectance for you, and doing the concentration system on a very low profile setup. And that's kind of one of the things that I'm looking at currently. And yeah, the glass wing butterfly, so the anti-reflective properties are shown in the left graph. So the blue line is the reflectance from glass, which is typically about 10%, unless you've got any anti-reflective coatings on it. And the glass wing reflectance is much lower. I mean, it's less than 2% for quite a lot of the spectrum, and then it starts to oscillate higher, which is due to the nanostructure, or the other nanostructures as well on the wing, the other parts. And then on the right hand side, I've got some results which show silicon on its own. So that purple line is silicon on its own, and then you've got glass on silicon. So this is the reflectance from 350 to 1100 nanometers, because we're just looking at silicon and thin film in this graph. But yeah, you've got a black line, which is the silicon with glass. You've got the glass wing butterfly, GW on silicon, which is the orange line. So the orange line actually does better than silicon on its own, which is impressive because you've got something you're adding on to the silicon, and it's actually producing less reflectance than silicon on its own. So that's the orange line, and it's got lower reflectance at the lower wavelengths and a little bit at the higher wavelengths. And then there's the thin film, just to give you an idea of other reflectance of solar cells, and also the silicon solar cell and encapsulant, which is that light blue line. And that's just to show you the effects of these materials that we add on top of a solar cell and how that kind of affects the reflectance. So if you're going to be doing a lot of research into trying to make a solar cell have a very high absorption, and maybe you've got a good anti-reflective structure on your solar cell, always take into account that that will alter once it's got some kind of sealant and cover glass on top, and it could, change it quite a bit. As I said before, because of this need for a lot more solar panels, a lot more PV technology. So if you look at if you've seen any talks or figures about where we sit in terms of PV technology, in terms of quantity, in terms of capacity, and you look at what the target has to be if we're going to meet any kind of net zero goals or net zero carbon targets, then there's an exponential increase that has to happen. And as I said before, with that, it's very likely that where we install PV technology isn't going to be in the optimum conditions. And also we're probably going to have different aesthetics and different transparency and all sorts of designs, so they integrate seamlessly into buildings or electric vehicles, etc. And so, and we were talking about earlier about indoor spaces, which obviously has a whole new set of conditions, and optics can kind of help with managing that or improving the multifunctionality aspects. And anti-reflective coatings will definitely be needed for all these kind of building integrated technologies, or technologies where it's not going to be tracking the sun and it's not going to be at the optimum tilt. It's going to be under all sorts of conditions. And that leads me on to beam steering. So beam steering is basically where you try to redirect the incoming sunlight so that it does become normal incidence or becomes more usable by your system. So for example, here in this slide is some images of some prisms, some refractive prisms, which you've got some angled incident light, and then the prisms have different geometries, but they all make the light go normal. So that then when it hits the Fresnel lens or your mirror, it's set up so that it's going to work perfectly. And these are just some images here on the left of how, with the change in angle, the light moves and can be accepted by the system, even at very wide angles of incidence. So down here we've got 50 degrees incidence angle, which normally for this system all the light would miss the this CPC type system, but actually it's getting captured still, similar to the condition at 30 degrees. So that's an example of that type of beam steering. You can also have, instead of having a structure on the first kind of layer, you can have these kind of, you can have bigger mirrors or bigger geometries. So this setup, same kind of CPC system, and this is all actually for a thermal device, but you can imagine how it would work for PV. But it's got these wings, these reflective wings on the edge, which move. So instead of the whole system moving and tracking the sun, you've just got these optics, these mirrors that move and funnel the light in, depending on where the sun is in the sky. And there's pros and cons to this type of system, but but for what they were trying to do, which was increase the number of hours in the day that they get a certain temperature of at the reactor, the receiver, they were able to significantly increase those number of hours by increasing the performance over wider incidence angles, which is shown by this kind of green line in the graph at the top right. So instead of it stopping at 60 degrees, it can increase, it can produce something all the way to 90 degrees, so the full range of incidence angles. And that kind of summarizes, or kind of brings me to the end in terms of the details. I have got this list of resources, which I think is very useful for anybody that needs to know anything about optics or anti-reflective coatings or irradiance maps and conditions at different locations. So PV Lighthouse, like I mentioned, has lots of calculators and simulations, and that includes AR nanostructures and layers of your PV. Some of these things are free, and I think some of them require membership. And they've also got SunPath calculators and solar spectrum calculators. And then you've got PVGIS, which I always get mixed up or always forget it because it sounds so similar to PVSYST. But similarly, you can get annual irradiance incidence and PV panel performance. And the good thing about it is that it's online, so it's quite good if you're collaborating with others because it's very easy to access. And then there's Solcast, which is also pretty useful. It has some very cool irradiance maps you can have access to. And it has kind of live and historical, more detailed irradiance data for different locations on the world, a bit more detailed than PVGIS or PVSYST actually. Or maybe it's comparable to PVSYST, but it can give you some live data, which is sometimes more useful because then you can compare it with your actual experimental outdoor data. So that's good. And then this other one, which if you are wanting to do anything with optics or refractive, changing the refractive index layers of your cover glass, this is actually a really good, very simple ray tracing online resource where you can just make some simple shapes and you've got some incoming light rays and you can change your refractive index and it will show you visually where light's going and where it's maybe getting reflected. It won't be able to do anything very accurate. It's just to play around with and help you suss out what ideas work and what they don't work. And I think that's the end of my presentation. If there are any questions.
Brilliant. Thank you very much, Katie. So again, a wonderful presentation, very comprehensive. You covered lots of different ways that we can improve the performance of PV with optical mechanisms. Again, to the audience, please can you put your questions through the Q&A and I will direct them to Katie. So to kick off, one of the first questions were regarding the indium tin oxide structures, the nanostructures. How are those manufactured?
Yeah, so I'll put a link of the paper in the chat for that because that describes it in detail. But they actually use it's like polystyrene beads that float on water, and they make them compact on top of the water, and then they use that to help etch. So it's etching, but pretty sure it's polystyrene they use that helps make the specific shapes they want in a compact way. But I'll copy and paste the paper link, which describes it in much better detail than I just did.
Thank you. Further on to that, so how does the aspect ratio of those structures impact the interaction you have with the light incoming in terms of thinking about design? Obviously, it's amazing we see these structures in nature just through evolution, but how do we when you're designing it for PV performances, what's the strategy for the aspect ratio?
Yeah, so there's a rule of thumb, which I think is like, I'm not going to remember what it is. You can look it up online. But the nanostructures, any feature needs to be a lot smaller than the wavelength you're wanting to, well, it depends what you're trying to do. If you're wanting the wavelength to see the structure, then any feature needs to be comparable to the wavelengths on the same scale. And if you're wanting it to be invisible, so have kind of graded refractive index effect, which I was talking about, then it has to be much smaller. Any single feature has to be much smaller than the wavelength you're targeting. And usually you would use simulation software to design these sort of things. So some of the simulation software you can use is Lumerical, which is, I think now, yeah, it's with ANSYS Lumerical. There's also some online simulators with a PV Lighthouse that help you do anti-reflective coatings. COMSOL, you can also use COMSOL for these. And that's the only ones that I know of. You can use other simulation software like TracePro and ASAP, but you just need to be careful that you're doing it accurately, because those systems aren't really designed for that nanoscale.
Brilliant, thank you. Another question. Hi, thanks for the insights regarding concentrated PV. Do you think that concentration is a parameter individuals should consider for their own PV panels, for example, on houses, balconies, or does this only matter for large-scale PV? So I guess, domestic, building integrated, or large utility, is it useful across? Yeah,
so it is useful across. Low concentration is used for building integrated systems. So it could be used for solar panels on rooftops or on in windows, for example, solar concentrator windows. I don't know how effective it is if you're retrofitting. So yes, you can design a solar concentrator system for buildings, and there's quite a bit of research into that. But retrofitting onto a solar panel that's already there would probably mean you'd have some practical issues of wind loading and things if you're just sticking a mirror up there, for example. But technically you could. I don't think you'd be allowed to for safe reasons. But you kind of see concentration happening with standard PV panels depending on their location. So we talk about it in terms of diffuse irradiance, reflectance from the surroundings, from other buildings, from the cement pavement, or from the water if it's by the coast. And that's basically doing the same thing. So that's concentrating light or increasing the amount of light that's hitting your panels. So you can think about it like that a little bit. So in solar concentrator research, we use the term 1 sun, which is for 1,000 watts per meter squared. But if you're in a location that gets less sun, then it would actually be 0.8 sun or 0.6 sun. And it's just a way of describing the irradiance that's incident, the intensity of the spectrum. And in some locations that's higher, sometimes it's 1.2 because it's 1,200 watts per meter squared. So technically you could say that's concentration because it's higher than the standard. But yeah, so it is useful for across the board. But retrofitting, not so sure. The systems need to be designed and then installed.
You mentioned about the concentrated PV and tracking systems. So are most concentrated PV integrated with tracking systems when we're dealing with large scale, or actually are they, what's the gain to be had by adding? Are there figures there about how much you can drop LCOE or performance by adding a tracking system?
Yeah, so there are some good papers out there that describe exactly that. So it comes down to the cost of manufacturing as well, though, of your optics, right, and what scale you're doing it at. So for high concentration systems, tracking is always needed. For low concentration systems, so the small optics that can be building integrated, they don't need to track. They could still, their energy output would still increase if they did track, but it would come down to the cost of the tracking versus the cost that you gain, the energy, cost of the energy that you gain. And there has been research into that, but typically you don't track when it's low concentration systems. Just, you can take out that extra component.
Brilliant.
Low concentration systems are anything less than 10 times. So if you're doubling the light, that's fine. If you're tripling the light, that's fine. If you're timesing it by 10, that's fine.
Brilliant. Thank you. Final question before we head to our lunch break. Based on your experience, which software program, such as Solar GIS, would be most suitable for climates similar to that of the UK? I think you mentioned a software that provides actual real-life data that can be used to compare own measurements. I guess just some insight into your own experience of which softwares are very good at utilizing the solar data.
Yeah, so it depends what you're trying to do. If you're only wanting some realistic weather data and realistic irradiance profiles to model the performance of your system, then any of them are fine, because any inaccuracy that any of them might have is very small in comparison to how much weather actually varies throughout a year. You know, so in the UK in summer you'll have some very sunny, clear days, but you also have some cloudy days, obviously. And similarly, you can have a good year and you can have a bad year, and that can mean quite a significant difference in your power output of your solar panel or your solar device. So weather changes a lot more than any uncertainty in a program. If you're wanting to compare the weather, the irradiance profile, theoretically, because you've got theoretical calculations or simulations, versus what you actually measured on a specific day, then Solcast so far, I would say, is the one that would be good to use, or an actual weather station data that you have on your campus, for example, or nearby. They're best used. The weather stations would be absolutely best if you had it on your campus or nearby. But depending what you're trying to do, it may or may not measure everything that you need. Solcast probably has, so far, as the only source that I've seen online that gives you all the kind of detail you need for a location you choose. And you, as a researcher, you get access to quite a bit of data for free, and then at some point you would need to pay for a lot more data. So it only gives you, you know, a certain range. You can download a full year data from it. You'd have to select the days. I'd only use that for outdoor measurements.
Brilliant. Thank you very much. Thank you very much, Katie. And thank you very much to the audience and also our other speakers from this morning. I think now we'll be taking a lunch break for 1 hour and restarting again at 2 o'clock. So thank you all very much for attending this morning, and many thanks again to our 3 speakers. And we'll see you all again in an hour. Thank you. Good afternoon, everyone. We'll just give it 1 minute for others to join us, and then we'll kick off. Brilliant. Yeah. Okay. Welcome back, everybody. Welcome back to the Research Methods for Solar PV 2023 workshop. Welcome back to those up here this morning, and thank you for joining us for those that have just arrived. This morning we had three wonderful speakers talking about organic solar cells, spectroscopy for PV, and optics for PV. And this afternoon, we're now joined by Dr. George Koutsarakis from the National Physical Laboratory. We'll be discussing IV measurements for PV, and later Dr. Silvana Oveit from NREL will be going over bifacial PV modeling. And again, as before, please put your questions and answers in the Q&A, and I will refer them back to our speakers. So I will stop sharing my screen and invite George to share his. George, I think you're muted.
I think now I'm unmuted.
Yes.
Okay, let me find the laser pointer. So hello everyone, I'm George Koutsarakis, and today I'm going to talk about IV measurements for PV devices. This seems like a trivial topic compared to the previous ones, but potentially 1 hour is not enough to cover everything here, as you will see. This is the general structure. We're going to talk about some basics about IV testing of PV devices, and then we'll present some information from the standards and specific cases of bifacial and metastable PV devices. And starting from the basics, in the dark, a solar cell is essentially a large diode, and this is its dark IV. When you're illuminating it, this IV starts shifting and you get some power. Essentially, you're supposed to be measuring minus current if you do measurements properly. And the more the light, the more the IV will shift, and we tend to flip it around and present the IV curves like this. So what can an IV curve tell us? Apparently, the maximum power of a photovoltaic device under the given conditions, short circuit current, open circuit voltage, and of course, maximum power point current and voltage. This can be pretty easy. So this is the end of the presentation. No, I'm joking. How hard can it be? It depends on what one wants to measure and how accurately. Essentially, there are different requirements for different purposes. If you are working on a new architecture or a new device, and you just want to check, is it working? Am I getting anything? How good it is? A crude method might be fine, and you will see something, so your device is working. If you want to use IV data for publications, you have to ensure that the results are reliable and repeatable. So you might be required to give a bit more effort on your measurements and requirements for the measurements. And of course, accredited labs, test labs, and people who actually make the measurements for efficiency records, they have to be very meticulous in their measurements procedures and use international standards. And this is some good practice for everybody to follow when acquiring IV measurements. Essentially, you have a device you want to measure, and you want to see its performance and compare it with other devices in the same field or with the same structure. So it is important to use a reference. Either this is a reference cell, either this is a calibrated light source. References are important because these ensure that what you're measuring actually is based on a national or international standard, can be traceable to the SI units, essentially. Of course, this is not a requirement for everything you do in the lab. It depends on what you want to do and how accurate your results you want them to be. So there are standards for IV measurements, essentially the 1694-1 that describes the current, how you can apply current voltage characteristics measurements of your devices. There are a lot of different standards mentioned in that document. So this is a whole series of standards that covers everything. This can be a very dry presentation, so I will try to be to make it a bit more fun just by describing standards. So let's start with standardized IV testing. And I am pretty sure that everybody's aware of the standard STC conditions. These are 1000 watts per meter, irradiance, 25 degrees junction temperature. The wording is important, as you will see in a bit. And the standard spectrum. So how do you ensure you are measuring your device under these specific conditions? You want calibrated reference cell, potentially calibrated temperature sensor, and a spectrometer to measure the spectrum of your light source. As I mentioned, 25 degrees junction temperature in the field under 1000 rarely, under 1000 watts per meter rarely happens. And what does this mean? If you illuminate your device under one sun, it will get really hot. So in order to get 25 degrees in the field, it might be, you might need a day under freezing temperatures and with the sun pretty high and the day being very clear. But you have to consider that historically and in practice, 99% of products in the field are silicon inorganic products that can be tested with flash solar simulators. So 25 degrees in the lab, it's pretty easy to achieve. Of course, when you're doing steady state measurements, things may become complicated. So these above conditions might be challenging to achieve in the lab as well. So what do we need for an IV measurement at STC? We need an appropriate light source, so a solar simulator or measurements are possible under natural sunlight as well. We need temperature control and feedback, electrical measurement equipment, of course, a source meter, reference devices, and don't forget, you will need the procedure. It is like beneficial always to have a protocol that you always follow when you're acquiring IV measurements. So starting from your light source, of course, there's a standard about this. Solar simulators can be steady state or flash simulators, and there are a lot of products in the market. These are some examples. There are large area steady state simulators as well for modules. This is one at PTB, and these simulators are extremely useful for making fun pictures, as this one from our colleagues at PTB. And there is classification for solar simulators for light sources. It can be AAA, if you have heard about this, which means they have a rating of A for spectral match, spatial non-uniformity of irradiance, and temporal stability. The question is, do you need a A+ or an AAA solar simulator? Classification will affect your uncertainties and how accurate your measurement will be. So this is what you need to consider when you are looking into a light source. Accredited labs and test labs will definitely need some very high spec light source, but not everybody is an accredited lab. And of course, classification affects price. So potentially, people can have a compromise between price and some compromise in their uncertainties. As we discussed, you will definitely need a reference cell to set the irradiance. So we will start from what reference cell do you need? There are a lot of reference cells available because there are a lot of different PV technologies available. So a reference cell with a spectral response as close as possible to your sample spectral response should be preferred. For instance, if you're working on perovskites, a KG5 will be appropriate. This is important, especially if you do not apply spectral mismatch corrections, which we will see in a bit. If there is a non-negligible spectral mismatch between your reference and your sample, you have to calculate the spectral mismatch factors. So why do you need the reference cell? I mentioned it just in the previous slide. You need to set the irradiance at 1000 watts per square meter. So somehow you need to measure this irradiance. This is done based on the reference cell's calibration value. As I mentioned, if there is a non-negligible spectral mismatch between your reference and your sample, spectral mismatch corrections need to be applied. This means you will result with a spectral mismatch factor, and you will use this to adjust the effective irradiance on the sample. So essentially, you will still be using your reference, but you will multiply the reference calibration value with a spectral mismatch factor to set the effective irradiance on your sample. And this is how you will get rid of the spectral mismatch, roughly, spectral mismatch difference between your sample and your reference. Why does this matter? This is just a slide of an example. So the light source you will use is not a perfect AM 1.5 spectrum, but what you are trying to get is a measurement of an IV curve under AM 1.5. Your reference cell also is not identical to your sample's reference cell, sorry, to your sample's spectral response. This means there is a spectral mismatch, and this is how you calculate it using the spectral responses of the reference of your sample and the spectral irradiances of your the light source and AM 1.5. You may be able to observe in this equation that if the spectral mismatch is zero, the spectral mismatch is zero if the simulator spectrum is exactly AM 1.5. This goes back to the classification for solar simulators. The closer a solar simulator is to AAA or AAA plus, the lower errors you will have due to spectral mismatches. Also, spectral mismatch is zero if the reference cell spectral response is the same as the specimen. So if you have a reference cell which is close to your or identical to your sample, then you will have no spectral mismatches. What the last sentence says, good reference cells are cheaper than good solar simulators. This means you should better invest in a matching reference cell than a AAA or AAA plus solar simulator because it's cheaper essentially. So we have calculated our spectral mismatches. What else do we need to do? We need to ensure temperature is 25 degrees. So temperature sensors should be located as close as possible to the solar cell junction. I mean, for standard cells, this is easy. I don't know how easy it is for R&D cells. So imagine a wafer-based silicon cell. As you see, it's in contact with a temperature control chuck, so it's relatively easy to control its temperature and keep it at 25 degrees and make some measurements. But I mean, in R&D, there are a lot of different device architectures, and you may have glass, you may have devices that have like some front contacts, some back contacts. So it's not always straightforward. So you need to be creative and try to get as possible, as close as possible to 25 degrees. And there are procedures to correct for temperature differences in IEC 60891. I will not go into detail into that. It will be pretty boring, but this is something that people should consider. Now we're ready to acquire measurements. Maybe not yet. We have to contact the device first. Again, always consider if it is possible to use 4-wire connections. Otherwise, there might be errors And most modern most modern source meters give you that option for wire connections. And I mean, a motivation will be that you might be underestimating the power of your sample. So it is, this is an extreme case, but it's not impossible to have such a difference. Now we acquire the measurements. Actually, not yet. In order, if you want to measure efficiency, you need to measure the area or mask your sample. So this is necessary when reporting efficiency, and there is guidance in the annex of 6094-1 of how you measure the area or the area that is unmasked. Don't use a bandbar mask. This is a joke. So now we will indeed acquire the IV parameters, and depending on your step and the range you have selected for a device, it might be impossible to hit exactly the Pmax, but it also might be possible that you will not get exactly the value at 0 voltage or 0 current. So the IV parameters need to be derived from the IV curve, and they are interpolated or extrapolated. So you will need a linear fit for the associated current, a linear fit or low order polynomial for the open circuit voltage, and also a 4-order polynomial for maximum power point. These, of course, fitting procedures will contribute to your uncertainties. So don't be intimidated by this. This is an example of an uncertainty budget that, for instance, a test lab has considered all of the different uncertainties when measuring current, voltage, and power. And there is a lot of things to consider here, as you're seeing, and everything will have a different distribution and also contribution to the total uncertainty. So in this example, there is an uncertainty in the power of ±3%. If you haven't considered any of this and there is no effort to reduce uncertainties, your measurement will most likely be much higher than this. There are a lot of other cases to consider, such as outdoor measurements. It is possible to acquire measurements outdoors, of course, depending on where you are outdoors. But this is described in the standard as well. There are cases where you need to acquire IV curves at non-STC conditions, such as energy rating measurements, where you take measurements at other irradiance levels or temperature levels, and of course, indoor conditions. There are additional complexities when measuring modules, because when you will have spatial uniformity, you will see some dips on the IV curve because of the bypass diode. So this is something to consider. And multi-junction devices, this is a completely different discussion. There are complications. You need to acquire proper spectral response measurements, and if you even move to multi-junction modules, things become complicated. So as we moved through how you acquire the measurements, now we'll look into some specific cases of, for instance, bifacial PV devices. There is a standard that it's also being revised about bifacial PV devices. Essentially, one needs to measure the IV characteristics of both the front and the rear side of a bifacial device. And additional parameters need to be measured and calculated as well. For instance, the bifaciality factor, phi, is the ratio between the associated current at STC measured from the rear side and from the front side. This is usually expressed as a percentage. And this is an example of a list of parameters. We recently had to measure through a round robin so that we are able to acquire all IV parameters of bifacial modules. I will not go through it in detail, but just to note that what is measured is the front side electrical parameters, rear side electrical parameters, front and rear electrical parameters at different irradiance levels, and bifacial parameters. There are some calculations for the bifacial parameters. So there are a couple of methods described of how to measure bifacial cells in the standards. You can have single-sided illumination where you measure both the front and the rear side. And in this case, you have to ensure that the rear side irradiance has a very low value, typically lower than 3 watts per square meter. This means you have to have baffles around your sample, but also a very non-reflective surface in the background, which might also be like further away. One needs to consider these features and measure them as well. A solar simulator with adjustable irradiance levels is required, and this is used to acquire and calculate the bifaciality, the bifacial power generation gain. I will not go into details here, but essentially what is required is to see how power changes at different irradiance levels. So, for instance, if you had rear side irradiance of 100 or 200 watts per square meter in the field, using the bifacial power generation gain, we will be able to calculate how much extra power the module will get. This is useful, of course, for modeling bifacial systems. Now, the background, especially when measuring cells, can be challenging to measure. This picture I showed earlier is, in fact, a bifacial silicon cell. And when PV cells are placed on the temperature control chuck, it is practically impossible to measure the rear side irradiance. So what one needs to measure is a transmission through the cell and the reflectivity of the chuck, and essentially ensure that your chuck doesn't reflect a lot, so use a black one, but also there can be corrections to that. There's another option to use an open rear contacting configuration, which makes the temperature control difficult, but as I mentioned, this is not an issue for flash testing. So this is a double-sided illumination system where you can have your sample placed like this, as you see in this picture, and you will have a specifically controlled rear side irradiance and front side irradiance. In this publication I have posted here from Juan Lopez Garcia, there are good examples of and comparisons of how different mirrors or rear side light sources, rear side reflectors, or even outdoor measurements have been considered for double-side illumination and testing of bifacial modules. In steady state measurements, temperature control can be difficult in such a configuration, but this is not a problem for short time measurements. Now, the question is, bifacial PV devices, when they're like semi-transparent or emerging bifacial PV devices, in this case, you can consider that for perovskites or OPV, for instance, the spectral response is usually up to like 750 nanometers, maybe 800, essentially the visible. And black materials exist that can have very low reflectivity in the visible. This means that potentially you can set up your measurements even at steady state for bifacial and semi-transparent devices. And again, you need to measure the transmission of your sample and the reflectivity of the measurement platform. One could question, what about multi-junction bifacial? I would actually ask, is there a multi-junction device which would perform better in a bifacial configuration than having a rear side like contact or reflector. This will be the discussion. And now we will move to how do you measure acquire IV curves of metastable devices, which might be a very interesting topic. Up to now, this is how the environment of metastable device IV testing look like, which is like the Wild West. It's not that bad, in fact. There is a guidance document, technical report, and there are methods published in the literature already. Although an established standardized method has not been agreed upon yet, there are reliable methods somebody can use from the literature that I will go through in a bit, which means actually there is no excuse to publish such IV curves as this one you see here, especially when reporting maximum power efficiency. I mean, potentially, if somebody wants to present something else about hysteresis or other effects of metastable devices, that's fine, but you cannot extract efficiency from like such IV curves. Don't worry, this is an IV curve that I generated. It's not from anyone's paper. This is a very short list. I might have missed something as well from recent work that people have presented how they acquire IV curves of metastable devices reliably and in a repeatable way, and you can tell between metastability and degradation. I will focus only on these two methods and give a summary of these methods just to show the general idea behind regarding how do you do this measurement. So the first is from NREL, and what is proposed is that it's called asymptotic Pmax scan. What is proposed is first you acquire a fast IV to determine the voltage bias window for the asymptotic Pmax scan, and then you may select 10 voltage points around this initial maximum power point voltage, and you also need to define a stopping criteria for your current measurement. So essentially, you set the voltage for each of these 10 points, and you monitor the current until it stabilizes. And you have set a rate of relative rate of change for your current, and once, for instance, it's this was proposed 0.1% per minute, you can log this point and move to the next one. And as we discussed before of how you determine your Pmax with a polynomial fit, having acquired all of these points, you can then get a Pmax. In the same way, you can measure the ISC and VOC, and what you get is an IV that has the relevant points, and you don't need to scan everything essentially. Still, this can take more than 15 minutes for its sample, and it can take even half an hour, I think, which means you have to consider other things such as light source stability, temperature of your sample, and degradation potentially. The second method is from ESTI. This is the European Solar Testing Installation at the JRC, the Joint Research Center at ISPRA. And this is interesting. So you start with the same step. Initially, acquire an IV sweep to find an approximate Vmax, and then you measure the stabilized Pmax using a power point tracking method, and again you need to define a stabilization criterion for your current. The difference here is you then move. I will show some graphs as well in a bit, don't worry. You then move and measure your stabilized current for different voltage steps towards source-circuit current. You measure in the same way stabilized source-circuit current, and then actually you go back to Pmax and measure the stabilized Pmax again. You do the same process moving to VOC, measuring stabilized VOC again, and then back to Pmax to measure stabilized Pmax. In this way, you have measured 3 times your maximum power point, and essentially either if you're coming from ISC or VOC, either essentially what is the history of the sample bias, you will see if you can get a stabilized maximum power, and this is what you should get for a stable device. As you see on the left, you start from the blue points, for instance, and you acquire a maximum power point, and then you move to the source recurrent, you measure a point, you acquire a point there, then back to the maximum power point, as you see in the red, and then VOC back to maximum power point, as you see in the green. And essentially, these points eventually should be close together for the device to be stable, which means you can apply a polynomial fit to get the maximum power point. If your device is not stable, maybe at the last point, you will never be able to recover your maximum power point, and then you may report the results, of course, but you have to also report that the device might be degrading. So what are the considerations based on what we just saw for metastable device IV acquisition? So first of all, and this is important, you might not see hysteresis with a fast scan. Here, in this IV curve, the total measurement time with a sweep was 20 milliseconds. This is pretty fast for a perovskite. Might be pretty slow for inorganic technologies. You might be able to see some hysteresis here, but we might not be able to observe it. Still, if we use the method that we just discussed, where we measure the maximum power point 3 times, you see that the real maximum power point is much lower, but it is stable because we managed to measure it 3 times, regardless of if we went to ISC or VOC previously. Measurements might take a long time. In this case, I think it was like 25 minutes. In this case, you have to consider temperature control and temperature feedback. So you need to monitor the temperature of the device. Try to repeat your measurements. This will show if there are like issues with the device, but also the procedure and the method you are using. And I mean, if things can get complicated. So for metastable and slow responding devices specifically, people can just consider measuring just the maximum power point if this is of interest. So you can have a simplified procedure, but close to like proposed methods from the literature. Also, note and report procedures used when publishing results. This is important because people can understand what you have done and how you have acquired your measurements. So, some takeaway messages. Always consider following the standard methodologies, of course, at a realistic level and depending on what levels of uncertainties you want to achieve in the lab, how much confidence do you want to have in your measurements. And try to consider all your different uncertainty sources. As I discussed earlier, this can be regarding like temperature, calibration of references, spatial uniformity of your light source, your instruments range and uncertainties. But when you consider your uncertainty sources, you might find errors in your method. You might find things you can improve to improve your measurements. And of course, there are different level of like worries people have if you're like a test lab or just a research lab that you just want to measure your devices. But you always have to have confidence in your measurements, especially when you want to publish results. This is an important one, especially for metastable devices. Do not alter procedures to buff cell performance. For instance, it's not very realistic to keep your device at a forward bias level and then apply a fast sweep back and forth and then measure the efficiency. This is not realistic because this is not close to actual operating conditions. And please try to follow some procedure that has been mentioned in the literature, and report your procedures when you are publishing your results. Exactly this. Report the details of your measurements and publications and the different steps followed. And this is important. If this is overwhelming, ask for help. People have published stuff. If you see a problem in the lab, probably somebody else had it before you. So look into the literature and try to find some help. I would say try to be aware of standards. It's not that everybody should follow all of the standardized methods exactly as they are, but it would be good if people were aware of standards. The PV community, I mean, most of the R&D community in photovoltaics, we do measurements in the lab. Either it's IV curves or it can be any other methods. In most cases, there are good practice guides, there are standards. It would be good if people were aware, if not following, when they can, the standards. So, any questions? More questions than before the presentation? We'll see. Thank you.
Brilliant. Thank you very much, George. Again, I think a very critical and important topic for many of us who are in this field. And you gave a very good comprehensive overview of the topic. Again, to the audience, please put your questions in through the Q&A and I'll refer them to George directly. One of the questions coming in is, I think this may be for more outdoor measurements, but hello, George. I recall you suggested using a reference cell to illustrate the spectral response. When it comes to measuring rear side irradiance, particularly on bifacial modules, are there any specific reference cell types we should consider? Additionally, given the non-uniform response of rear irradiance, where would be the best location to position the rear side reference cell?
Thanks, Yazan. This is a good question. And I would say this is a good question. The rear side irradiance has a very different spectrum than the front side irradiance, especially, for instance, in the UK, where you have grass. You might see like most of the visible spectrum disappearing, and this will create a significant spectral mismatch. Are there rear side irradiance reference cells? I'm not aware. It might be. There might be something that I'm not aware of, but essentially, again, I would say try to get a reference cell that is as close as possible to the PV module's rear side spectral response. Of course, this means that you will have the data of the rear side spectral response of your module. This is not always the case. Again, these data should be available if you want to do. I guess you ask because you want to do some proper modeling. About the position, I mean, depends if this is a ground-mounted system, a tracking system. I think there might have been some literature on the different and how different positions affect measurements. But yeah, this is a good question again. It will depend on the system configuration for sure.
Brilliant, thank you. I had some questions on IV standards, and I mean you've got a lot of experience in this. How long does that process take? Because obviously bifacial, there's been a lot of work done to get these standards on how you measure current voltage. Perovskite cells coming through, again, standards will need to be done. World record perovskite silicon tandem just came very recently, hitting that really high on those NREL charts. how long does it take to actually find a set of procedures for measuring that new cell technology and standardizing it so that's widely used in all the labs? And what are the steps in that?
It takes a long it takes a long time. Essentially, when there is a when there is an issue observed, then there are you need to do the research, you need to propose some solutions, you need to discuss with other active people in the standards, and then eventually there might be a project where a revision is proposed to current standards or a new technical specification or standard is proposed, and this also has to go through different versions, and there is always like a negotiation in the standards of what, I don't know, test labs want, what the industry wants, and eventually when there is a final version, again it goes to the committee for reviewing. And I mean, this might be like it's in the range of years. It's not like months, it's years, or I don't know, more, maybe sometimes 5 years. It depends on the standard. Sometimes things happen faster, again in the scale of years. Sometimes they happen at a slower rate.
So then the efficiencies that we see for particularly the record-breaking cell structures in the new technologies, which haven't had that time length to have any fixed standards, how trustworthy are these results?
I mean, for instance, NREL has published how they measure the efficiency of the perovskite cells especially in this publication I posted here, previous one. This is they have published in detail how they do it. I think the name of the publication is like calibration procedure for performance of emerging PV devices. So this is definitely trustworthy. And in that publication, you can see how this method applies to different samples. For instance, you will get trustworthy results regardless of what technology you measure with this method, but it is appropriate specifically for emerging PV devices.
Another question. Hello, thank you for the information about IV curve standards. Do you think that open science is a help for standardization? That's from Maximilian. And again, actually, thank you, Maximilian. Lots of great questions today.
Yes, thank you. I'm not sure what the question is about, but what I will say is I understand like standards, you have to pay to buy the standards. So there might not be like accessible to everyone, to everybody that works in R&D on like PV devices and materials. Yes, this might be a challenge, but usually standards are a result of some research with evidence, and there will be publications of procedures, publications of best practice first, that then things will move to a standard. So I would suggest people should not like wait for a standard to tell them do exactly this. Look into the literature, there are solutions there.
You mentioned something about when we were doing the metastable devices, it taking quite a long time to actually get the correct results, often 25 minutes of measurements. Obviously, that's not something that's going to be feasible as you try and get through lots and lots of cells in industry. What are the strategies for trying to get that time down?
This, I mean, I would not expect that the industry will measure every single cell of an industrial line, but when a test lab acquires a sample and they're asked, can you tell us what is its efficiency? They have to find a way to give you a reliable answer. So if it takes 20 minutes, it takes 20 minutes. I mean, what can be done? Maybe potentially somebody can ask, I only want the maximum power point. I don't care about like ISC, VOC. I just want the maximum power point to find out the efficiency, and that's it. This might save some time, essentially. But of course, when measurements last longer, they have a higher cost as well. It's different to have a flash and do the measurements in like 4 milliseconds, and it's different to do when measurements last like 20 minutes. And there are other like considerations. As I said, I mean, temperature is the most important one, and stability of your light source as well. Can a xenon light source do that? Maybe sometimes, but you have to monitor it. In especially in the standard for IV curves, it is mentioned that when measurements take long, you should monitor your irradiance, not just like measure it before, place your sample and measure it after. You have to monitor your irradiance during the measurements.
Can you, when you were talking about different errors, what are like some of the key steps that those of us in our own labs that are trying to do some cell measurements, what are the most common errors that you've come across that we can take on board when we're trying to do cell measurements just in our own labs rather than in a, you know, a standardized lab conditions?
Yes, good question. In practice, I would say you can start with the simplest things. I'm looking for the uncertainty budget. What are the things you can actually improve with not a high cost, for instance? So I would start with like 4-wire measurements. I won't assume that everybody does this, but in case you're not doing it yet, this can be useful. Temperature control is important. I mean, being able to have temperature feedback when you're doing measurements is important. As the temperature and humidity group at MPL says, everything is a thermometer. Everything changes with temperature. And if we can quantify that change, we can use it as a thermometer. The same is true for PV cells. So you have to ensure you're either like keeping it at 25 degrees or you are measuring the difference so that you can potentially apply some corrections. Check your instrument's uncertainties and potentially try to use the proper range for your measurements. I mean, this might be very trivial to some, but I have seen people that do not like set the range, essentially the dynamic range when you're measuring the current. So you might be using a range of like 1 amp, but you're measuring current of milliamps. So you lose a lot of dynamic range, which means a lot of standard deviation in your measurement. So yeah, I would say start with the simple things and what you can improve without high cost. I mean, the first step would not be to buy a very expensive AAA solar simulator. It would be to improve the simple things.
That's so spatial non-uniformity is leading to one of the largest, right?
Yes, I mean, it depends on the solar simulator. So this might be, I mean, this is from a test lab we're working with, but this might be for a module. And when you move to such large areas, there will be spatial non-uniformities. It's much more difficult to have a very uniform area as much as the size of a module.
Yeah, I was going to ask you, like, how, as you transition from cells to modules, how much more complicated does it get to get those IV curves in a fair way?
I mean, there are additional challenges. I mean, in one of the slides, I had like modules. These are completely, I mean, not completely different, but there should be additional considerations there because you have bypass diodes, your IV curve might be affected by spatial non-uniformities. And I mean, you can also consider how can you will need a steady state solar simulator when you are going to be measuring metastable devices like PV modules, because you will have to have a stable irradiance for like, I don't know, half an hour. So this might be challenging. I mean, are there facilities in the UK for that?
For the metastable devices, are some of these challenges, can they be tackled by adding and supporting with other measurements like PL, for example, to help estimate some of the potential errors?
I mean, you can definitely, and we have published something recently, look into how photoluminescence looks like when you're applying IV measurements. But specifically, if you want to get an IV curve, essentially, why are you doing this? You want to get a measurement of your maximum power and potentially some other IV parameters to calculate the fill factor and efficiency. So this is the aim, which means all of your measurement is designed based on this aim. If you want to have additional measurements like PL that you mentioned, it's fine for like diagnostics and to see what are the problems in your device and why maybe it doesn't perform as good as you expect it to be.
Brilliant. I've just got one final question. I think we've still got time. Yeah. We had this challenge when we were measuring back contact solar cells in terms of the number of fingers used for actually probing when you're doing your IV curves. Do you have I mean, what are the standards for that, and any advice on how you would approach that?
Yeah, so specifically for silicon cells, essentially, I mean, as many contact points as possible is the is the advice, because they will reduce your resistance. If you saw in the exactly in this image, not the Batman one, this one, you see there are a lot of points, contact points there, and actually in later systems there are even more than that. This can be considered pretty sparse. So using the for bifacial cells, using the single-sided method, you will do this for the front, and you will do this for the back as well. There might be cases that your rear side bus bars are not the same as your front side bus bars. I mean, test labs have a lot of different mounts that can accommodate for a lot of different bus bars. I know it's like a big cost for like a lab, a research lab, but I mean, when you're a test lab that offers this as a service, you have to accommodate for all of the different possibilities. But having said that, in the silicon industry, there are a lot of different options, but not a ridiculous amount of options. So once you have like established, I don't know, a contacting scheme, it will most likely work for a lot of different samples.
Brilliant. Thank you very much, George. Thank you for answering all the questions and the wonderful talk that you gave and your time today. I'd like to now invite Silvana.
Hi.
Hello. Good morning.
Good morning.
Hi. Thank you for joining us. I know it's very early over there.
Well, it's 8, so that's great.
Brilliant. If you want to just share your screen.
Okay. 1 second. Let me close all of the other things that don't need to be open for the presentation.
Brilliant. I think we can see the wrong.
Oh, that's true. Sorry. There we go.
Perfect.
Good.
Yeah, so I'd like to introduce Dr. Silvana Oveit from NREL, and she'll be talking about bifacial PV modeling. Thank you very much, Silvana.
Great. Thanks for the invite, Tasmiat and Christopher. And hello, everybody. I am a little bit sick this morning, so you will excuse me if I sound funny or have to pause. But I'm excited to be here with all of you. I love the concept of this research methods event. Firstly, to introduce myself, I work at NREL for the last 5 years, a little bit more if you consider the graduate internship. And I work mostly on bifacial PV. My background is electrical engineering and optics. So I got my PhD from the University of Arizona. I am originally from Mexico. That's where I grew up in the north. There's an image there of some of the indigenous culture dance that's from that region. But my family is from Uruguay, so in South America. And just a little bit of myself, I love astronomy, and I live in Colorado, where NREL is in Golden. So it snows a lot, and that's my husky. That's my LinkedIn. If you want to connect, please send a note. Don't send empty invites, or you will be ignored. Cool. So the goal for this session is to give you some overviews of key knowledge essential for postgraduates, postdocs, and industrial researchers, right? So I added a bunch of topics, so we'll see how long we go through this. And I will pause to go through the Q&A throughout, so please, or the chat, so please post any questions. But first of all, a little bit of motivation, putting it all into perspective, right? And this is something that you might know, perhaps not for the US one, right? But in the US and in the world, there are decarbonization goals. There's a lot of solar deployment goals for the next 30 years or so. In the US, we want to at least install 1.6 terawatts. That is, I mean, we reached globally the 1 terawatt mark last year, right? So that means ramping up from the current installs that are happening at 20 gigawatts per year up to 60. So 3 times increase on how fast we are deploying solar, right? And this is not only deploying, but also manufacturing. So you can see what the challenge is there, because it's not only the US, it's the world that has this big deployment goals, right? So depending on which person, literature you see, and these are coming now every year, every couple months, right? There's different goals between 15, 16 terawatts to all the way over 70. And this implies going at least twice of the deployment on a global scale, scaling that, or 5 times what we are doing right now, or up to 23 times. So this is quite a challenge for sustainability for us to make sure that we have good PV modules, that we are spreading how to use them the best to reach these goals. In the US, we have adopted a lot of bifacial modules, and this is due to some of the tariffs that the government applied to modules imported, right? Now, it is also because it is a trend worldwide, and because of the gain that you have, but certainly the economics help. And now, not only in the US, but worldwide, the price is very comparable. So at least on the utility scale, almost 3/4 of what we installed were bifacial PV. And why is that? Because, as I mentioned, it gives you energy yield gains, right? So you're not improving the efficiency. It's high efficiency, just as the monofacial, but you're adding all of this extra input that can increase your production, right? So, and especially if you then join it on top of tracking, then you are really improving how much energy you are expecting, and that lowers your LCOE. So worldwide, this is from the latest ITRPV presentation, we had already since the last years projected an increase on bifacial cells and bifacial modules. Basically, even bifacial cells are going into monofacial modules. So even with the backsheet, that's still where the production is going, to make more bifacial cells and definitely more bifacial modules. Now, in terms of technology, and I wanted to touch a little bit on this, is PERC is most of the market right now for bifacial. And we have a couple other options showing up, right? So besides PERC, we had Topcon and silicon heterojunction that are projected to start gaining more market share. All of this on the bifacial side, right? Topcon and silicon heterojunction are definitely bifacial. So this projects that they are definitely going to start representing more of what is to come on N-type wafers. For those of you not very familiar with cell types, right? So we have the PERC is usually in a P-type wafer, and we are achieving bifacial gains of, I think, 70%. It's kind of like the average right now. And the upcoming ones, some of the things that they're trying is to increase that bifacial gain up to 90% for the silicon heterojunction. So they have that slightly high efficiency and bifaciality that they're seeking to do. Now, again, they are very new markets being deployed, so we're still hoping to see under reliability and the performance of this to more extent. But that's where we're at. And we're also obviously keeping an eye on new technologies, right? So we are going to have a bifacial cadmium telluride tandem or perovskite silicon tandem. So according to the ITRPB, we might be seeing some of those bifacial tandems by 2026. Cool. So that is the market. We are growing a lot. We have various options of cell bifacial cells. Now, this slide is from 2019, and I am just putting it back again because we still have the same challenges or questions, but we have a little bit of more nuance on the things that we're looking into this, right? So the performance models, I feel we've been beating that horse to death, but there's still more details to look at on how we use the loss factors, if they apply for all locations, etc. The standards that George talked about, they are well established for how to measure the bifaciality, but capacity testing, so that is when you actually deploy the field, is still being figured out or trying to convene all the stakeholders. And then there's still a lot of questions of albedo, like should we optimize it? Do we do different things, etc. So there's a lot of area to play in research and in industry. And obviously reliability, but I'm not going to talk too much of that today. So in terms of the performance models, so understanding the modeling of the monofacial modules, it's pretty well agreed on. So the performance, because the light is just reaching the front, we have models that calculate irradiance and then the module performance, right? When we add the bifacial, we're adding this light on the back of the module, which is often reflected by the ground. So then the spectral qualities might change, or the self-shading as the sun moves, angles, etc. So that complicates a little bit really knowing what that rear radiation is. But in general, whatever you calculate that rear irradiance to be, you have to multiply by the fact that the rear side of the module is not as good as the front side, because just it is not as good in capturing those electrons, or there may be shadings from the junction box, or there's various aspects that make it slightly less efficient. So that is the bifaciality factor, right? So you multiply or reduce the rear radiance by the bifaciality factor and use that as your input to your single diode model, just the addition of those two irradiances. Now, if you go and read papers, especially the older ones, you will see some very wild numbers of how good bifacial gain is. Bifacial gain is how good the bifacial is compared to the monofacial. And as a basic thing to teach all of you, or to hope that you keep in mind, is that bifacial gain is a tricky metric, right? You have to put on your skeptic glasses and really see what people are doing when they measure their bifacial gain. Because first of all, bifacial gain can refer to the gain of irradiance only. So that first layer of like how much more irradiance you're getting, or fully after the electrical model. So what is your performance, right? So once you calculate the module is producing X watts or energy, watt hour, what is that gain compared as? So we have a bifacial field in NREL where we have deployed 5 different technologies to explore this. What is the bifacial gain? We're also exploring other things like the degradation, the instrumentation, etc. All of this data, by the way, is open source, open data. So if you have anything that you want to model or compare or look at, go look at the data set. So what we have found with these various technologies where we have 4 PERCs and 1 silicon interjunction is that the gain is more around 5 to 7%, 6 to 7%. This is 3 years rolled up of the bifacial gain by month. You can see that on the summer, the silicon interjunction, which has a better temperature coefficient, is outperforming the PERC. So you can notice that, but in general, we are getting not 27%, not 50%. It's more like 5 to 7%. And that gain is more realistic because on this field, we have enough rows to do self-shading, right? So this is one of the things to look at when you're seeing bifacial gain on papers or articles is the experiment a single module or a single cell, right? Because that shading there, it's very little. So that rear radius is not blocked by a lot of things. But when you have a real field utility scale, which is what we ultimately aim for, right? We ultimately aim to put all our devices on a lot of fields on making a lot of energy together. There's a lot of self-shading from the row, from the module, from the other rows, from the racking. And that can reduce up to 150% that rear irradiance. So that's the first caveat there. It's like, if you have an experiment that's 1 single cell, you might not be representative of that steady state. Now, the other aspect of bifacial gain is that it is a relative metric, right? So if you look at this plot here, which is from our field 2 days there, this sunny day, you can see, oh, wow, that bifacial is like producing a lot more power than the monofacial. It's clear, right? That's visually clear. However, the day that actually has the higher bifacial gain in this is the day on the left, the day that's cloudy, because it is relative to what the monofacial is performing. So yes, do you think self-shading can be reduced by sunlight concentration reflection by mirrors? You can definitely use mirrors or albedo to increase the rear shading. But again, if you're doing your experiment with 1 mirror and 1 cell, you're not going to be steady state representative of what will be on the field, which is what I'm trying to say. So you will have to like have a bigger setup or put fake cells or fake modules to make like a bigger array to really represent that self-shading. That is answering to Maximilian's question on the chat. Same thing with the bifacial gain. This is a snowy day, so you can see a couple cool things here. So the monofacial here is not producing anything. The bifacial is. And the second day, the bifacial, because it is producing as well as this particular one being frameless, it sheds the snow a lot faster than the monofacial. So if you compare to 0, that bifacial gain is like really shooting up to infinity, right? So that's tricky. Same thing if you look at bifacial gain in an instantaneous manner, right? Compared to front POA irradiance, you're going to see very high irradiance gains at very low irradiance. So that is early morning or cloudy days, as we were saying. But most of the actual bulk of the energy production happens when there's more sun, right? And the bifacial gain is lower, closer to the 6-10%. Okay, so takeaway is really think about how bifacial gain is being measured and what it means. But overall, yes, the bifacial modules have that extra input, have that extra power generated. Good. Any other questions up until now?
I think there's one in the chat from George.
in the chat. Okay, I have the other one open. Chat. No, here.
Can you read it out?
There we go.
Okay.
Hi, Silvan. Are the strips in the outdoor bifacial setup connected to an inverter? In real system, clippings will reduce bifacial gain even further. That is very true. The number of bifacial gain in real systems are around 5% or lower even. Yes. So we are connected to an inverter. We are not clipping at NREL. That's why we are seeing the 5 to 7%. And yes, the clipping can definitely reduce. But that, I guess, putting into perspective, yes. So 3 to 5%, 3 to 7% are real numbers that you may see on the field. But yes, a lot of the bifacial gain might be on that sunny day, on the middle of the day, and that might get clipped. So that is a lot of the considerations that go into designing your system, right? So you can do various things, like to improve your LCOE. You can use less modules to obtain the same power, or you can keep that high clipping if what you're interested is on producing more on the mornings and the afternoons. So yeah, clipping is a very interesting effect to consider. Cool. Okay, so let's talk a little bit about models. There are basically now two models approaches, two flavors of modeling, right? We used to have some empirical models, but those were very early bifacial field. Now we use either a view factor model, which is based on equations. You calculate the irradiance, the direct and the diffuse on every patch of the ground. And then from the patches of the ground, you calculate it to the modules. It's very simple, it's very fast, and it's very common. It's behind SAM, that's the System Advisor model from NREL. And it's also behind like PVSYST. And I keep seeing bifacial view factor pop up everywhere because it's apparently a great master project, even though it's reinventing the same wheel. So yes, the equations have been known. They're from thermal transfer, so they're from the 60s. So anyway, I did wanted to stop for a second and show how you can model a bifacial if you haven't done this on a tool. I am using SAM because it is open source and I had it more available, right? But when we make a new project, there are various things that we can modify for the bifacial. Oops, sorry. Can you see the SAM screen?
Yeah, we can see it.
Perfect. So SAM, you can download it for free. It's a full due diligence software like PVSYST. So here I'm just doing a residential owner example, right? So the first, here on the left, you have all the things that you can modify the categories. The first one is selecting your weather file. I'm just going to leave the default, but I did wanted to show that you can do various things with the albedo. You can either set a monthly value, which PVSYST is still using monthly values, or it can grab the albedo from the weather file, so hourly points, which is great because that leads to some differences, right? But now there is also the option to set up spatial albedos. So for people that are doing albedo optimization or agri-PV, you can also set up saying, okay, so this is 1. So this is going to be my very high albedo on the center of the row, and 5 is going to be 0.2. So you can do that now, which is pretty cool, pretty nifty. On the modules, you can select the bifacial modules, like sort them by bifacial modules, select whichever module you want. Let's say a Canadian solar. And now we're starting to see, this uses the SEC, California Electric Commission database of modules. So we're starting to see modules like those big format modules above 500 watts, which is really cool. And so you can tell it is bifacial, but you still have to activate bifaciality. There's various things that matter for bifacial modeling, which is how high it is from the ground. So you set that up here. The transmission factor helps you increase area irradiance when you have more module to module spacings on the row or cell to cell spacings. So you can calculate that area of transparency versus what you actually have installed. Other things to modify is obviously the system decides how many strings and modules you have. If you have backtracking, what else for the bifacial? So the new thing also is on bifacial is that SAM and PVSys give you loss factors that you can use to correct for some losses, right? So that self-shading, that shading from the torque tubes, we have a shading factor here, or we also have an electrical mismatch factor that now can be calculated internally. So instead of asking you, hey, what do you think is your loss from the cells having different irradiances on the back? So there's actually an equation that got published on 2020 by our group, and that is into here. So that takes away one of the loss factors that people can calculate. Anyways, let's run the simulation just to show you some of the also new results that you can get from this. And if you want to type questions while this goes, it should be pretty fast, but almost there. Okay. Cool. So on the results, you obviously have all the data that you might want here, but I did wanted to go to the spatial results, which is now showing the ground irradiance for those of you that are going into agri-PV studies, and the module reader irradiance, right? So we calculate the irradiance on at least across the module on like 10 positions, I think. I have to check. So that tells you, okay, across the module from the edge to the top, that is the distribution of the irradiance for every single hour in the year modeled. So that is some nifty things there to look. And all of this data is on the data tables, but they plot it for you here. Cool. Okay, that was my little segue into SAM. The other option from ViewFactors is to do a ray trace, which NREL maintains bifacial radiance, or developed bifacial radiance, which is a ray tracer. Now, it is definitely more complex and more computationally intensive, even though we have a GUI. But it is often used to validate or compare to the ViewFactors and to obtain this loss factors that people are very interested to. So that's one of the things that we do a lot, is try to come up with the tell people about the shading factors, because you can represent more accurately the physical layout of the cells, the array, the shading, the racking, also the spectral versus diffuse components. So anyways, there's been lately a lot of round robin comparisons between models. Finding, first of all, it's very interesting to see how we do not agree on how to center or model or some position on data, right? So data can be, if you're collecting minute data and labeling it from 8 to 9 at 8, that is left label, or 8 to 9 and you put at 9, that's 9. And that goes into the software's not knowing, oh, my sun position should be at 8:30 or 8 or 9, and leads to this same power production, but all over the hour, right? So you can force align them and they look a lot nicer. But that's one curiosity that the modeling community has not gotten to agree on. But there is good agreement for the front, and there is an okay agreement for the back now, at least between 4%-ish for most models. There's a lot of also non-commercial modules on this particular round robin that I'm showing here. The thing is also the rear radiance again gets multiplied by that bifaciality factor. So in general, even if we have disagreement from what it should be, right? So this, we have the model versus the measured. It's underperforming what is the modeled. When we get all the way to modeling the power, we still fall on a good agreement, good mean bias deviation, because again, it gets reduced by those losses. So something to consider about, but not super worry, oh my God, all of this is going away. Now, to complicate the modeling is the fact that when you measure, you can measure a lot of different things, right? So if you place your reference cells on the edge versus on more centered on the module, or on the east edge versus the west edge, then you will see different shape, different irradiances through the day. right? Up to 13% difference from the average. And then that gets even worse when you consider that you may have edge effects, right? Even if you have if you don't have a steady state field, like a big enough field of at least 7 rows by what, 10 modules or something, you will get a lot of extra radiances from the edges, right? So I guess I saw Yasan's question earlier. I was like, where to place reference cells? Where there's not a standard on that, but there's definitely some best practices on the field that I'll get to in a minute. Oh, I don't know why I placed this. Oh, I was talking. Yeah, so you can use loss factors to also better correct your models to match your data or to better qualify some of the setups. 2 of the main loss factors are the shading loss, which is basically, as a first order, you can use the torque tube diameter divided by the collector length, right? And that is, if it occupies 10% of your back irradiance, then that's the value that at least PVSys documentation suggests. One thing that people can do is also, when they install, is like they ask their tracker, what is their value for their tracker? And those trackers often come to us and ask us what the value is. And we obtain those values by the ray trace, right? So because specifically also when you have like 2-up configurations or different, that rear radiance is affected, right? There's some reflections involved, etc. So we can calculate that. And this is also the electrical mismatch factor that there is not a lot of guidance on what to put. So you can do a full cell-to-cell level modeling, or you can use this equation. You can also invent the value, right? But you can also use this equation. This is the one that's on SAM internally when you activate that click. Basically, on this paper, we associated the distribution of irradiances across the back of the module to what the electrical mismatch loss will be. Cool. So on standards, George already did a great job on talking of it. I wanted to mention, I guess, we have standards for various things on PV, and they are all being modified for bifacial, right? So he talked a lot about how to measure a module, right? But there's also qualification tests to make sure that they are resisting enough on the environment, or that they will last out there, etc. And I guess adding a little bit fun throwback Wednesday is looking at some old data sheets, and the reason why it was so important to come together with this standard for measuring bifacial is that everybody had different way to report their bifacial gain, right? So this old data sheet from Longisolar had STC for the front and the back. Okay, and yeah, so it became a little bit difficult, and you can see that there's no bifaciality here. You can calculate it obviously from this measurements. This other company had a bifacial factor and just had STC, but there's nothing else measured with the rear, right? So you just have to take the bifacial, the rear side performance to be that. And then there are other people that started to say, well, maybe we should come with a joint front irradiance bifacial, and this is pre the standard, so there was still no agreement on what the irradiance levels are. As George mentioned, now we have, you can first you measure to calculate the bifaciality so that it's measuring the front and measuring the back, and it's the minimum of any of these measurements, usually the Pmax or the current. And then you calculate, because it's very uncommon to have this fancy like solar simulators that can show from the front and the back, or that have the trough, right? Most commonly you have a solar simulator that's just coming from one side, and what you do is you correct that irradiance level by 100 times the bifaciality factor and 200 times the bifaciality factor, right? So that's how you can achieve it on any solar simulator, and the round robins of the laboratories have shown that it is a great method to use, or a good method to use. This is a data sheet, a more recent data sheet. And I want to show this because, again, this follows that standard, right? So it gives the bifaciality coefficient that they calculate on step 1, and then it gives the bifaciality production at 100 times the bifaciality factor and at 200 times the bifaciality factor, right? So that is, I'm showing this because I got an email from a researcher a couple of weeks ago, and they were like, hey, are they considering the back measurement? Are they measuring the back on this? And the answer is yes, they are, because they're using the standard. So they're technically just shining light on the front, perhaps, because they don't really specify which method, or I guess they do. Frontal irradiance, yes, it says it's on the frontal irradiance plus the bifaciality, right? So they have the standard simulator, but they're still considering the rear addition of irradiance. Cool. So I promised this a little bit earlier. So there is no standards on then once the modules are on the field, how do we really measure that rear irradiance? But there are some common practices, right? You definitely want to have some rear irradiance cells, reference cells, right? Front one is a given for any site. You want for bifacials to have some reference cells on the back. There are some novel methods of putting some reference cells, kind of like a rotating albedometer on the toric tube unobstructed. And there's also a big push for reference modules nowadays, which are bifacial, and then you take measurements from blocking the backlight, the backside to calibrate and use that as your reference. So that is a novel also technology. But ideally, because of all of this variation across the module irradiance and across the row, it is suggested to, oh, great. Just bringing up a comment from George. Yes, sorry, I haven't updated those, or I don't follow the standards as closely as you, so that's great to know. The bifaciality from short circuit current is the right one and not the one for power due to nonlinearity issues. So that is something great to be aware. I will update my slides. Thanks for the update on that. Going back to where to measure rear irradiance. Ideally, not the edges, because they differ a lot from the average that the module is seeing. Ideally, not underneath the toric tube, because the toric tube will block its light, or on the toric tube, because then you are not on the plane of array. So you're seeing also less irradiance because you're closer to the ground. And based on a fancy module that we have, a reference module, we calculated and we measured that the best agreement with the average is actually like 30%, 20% from the edges having 2 sensors. So that gives you very close to the average of the reference. So in general, whenever people ask us, we say, have a couple of reference cells and place them at different positions, right? Otherwise, you might be very biased towards one of the sides. This is the module that was mentioned that was used for this. Here we have each row of cells is connected together. And it has 12 junction boxes. So we can tap the irradiance levels on each of these rows, right? So that gives us this differences, and we see definitely the toric tube shading on the center. At this point, there is some more reflection from the ground, etc. So this is the data that we use to like validate where to put some of those reference cells. Cool. Any other questions up until now? How many ambient bounces on the sensor have been taken into account for reverse ray tracing on back of array? I don't recall what. Ray tracers usually have some parameters that you can set of how many times a ray can bounce before it, because every time that it encounters a surface, it will start splitting or losing energy. So you only do so many bounces. I don't know. I will have to go see what the bifacial radiance setting is for that. but definitely we don't model inside of the sensor too. We usually just measure at the surface. And then, because we do have the option of adding a glass surface, which then will add a sort of in the sensor. Geometry of bifacial modules and or modular arrangements. Are there other geometries imagined in the bifacial community if you think about flexible solar modules, like OSCs, organic solar cells, or other thin films technologies? Huh. Let me think about this. I mean, I've definitely seen studies from the optical perspective, putting them on concentrators, right? We see in the front and then on the back, or doing some more complex things. But not that much. Most of the deployment follows, but modifies when the facial tracking deployments. I mean, they have to be modified because a lot of them are frameless, so you need different arms to support them. Higher clearances also benefit them, etc. So not so much in geometries, but definitely in applications. There is a lot of interest on vertical bifacial, as well as bifacial for higher latitudes, because again, they have this higher bifacial gain on more cloudy locations or cloudy settings. And the fact that they take advantage of all the diffuse irradiance, right, that benefits on higher latitudes or snowier places where the back's not going to be covered with snow, so the front, so we'll start producing power, heating up, and help with the snow melting. So there's some interesting applications there, and also on agri PV, right? Cool. Let's talk a little bit about albedo. Not too much because it's a very wide topic, but you must have heard that reflectivity of the ground is referred to as albedo, and that is a value that can vary with time, but it also varies with spectra and with angle that you're measuring at. So it's a complex, very complex measurement that often gets summed up to one value, something between 0.2 and 0.8. And it is important because obviously if the ground has more reflectivity, more light will get to the back of the solar modules, right? Even if you put like a mirror, that one there, right? Now, regardless of the albedo, even at seasonal albedos of 0.2 or less, there is bifacial gains for the whole world, even with seasonal albedos. So, because you're still capturing a lot of irradiance reflected. Now, the difficulty with albedo is that we don't always have data for the sites that we're placing. We can assume based on those values, there's a lot of places that have tables of what to use. But a lot of the weather files now have also albedo, so both the ground measured and satellite measured. I will suggest to always prioritize, or ideally prioritize, ground measured data, weather data, and albedo, because obviously the satellite is making an average of a bigger area, and it's also encountering some problems with measured data with snow, or it's a little bit more finicky, I will say. The uncertainty has been, it's wider than the locally measured data. So if you have local measured data available, that's the best. Also, to put an albedometer on your site, it's practice on bifacial fields. Now, there are various ground modification concepts that people are exploring now from the research and industry side, because they're interested on increasing this bifacial gain, right? So you can have spray on or roll out tarps, or maybe put gravel that's very white. So there's various methods. We explored one at our bifacial field to see if there was, instead of covering the whole area, if there was a way to cover just a section and improve the bifacial gain, right? So covering the full section gives you a plus 5% gain in bifacial performance. So on top of what you already had. So this is definitely good, but it also costs to put, and it also soils, so that adds to the O&M. But at the same time, it might also prevent some of the plants from growing, so it may reduce some O&M from mowing. So there's a lot of considerations, but I will suggest or say that we have a PwC paper coming with a very in-depth look at the modeling and the cost modeling of reflectors, and if this can be optimized. So basically, yes, you can put reflectors as long as they're 2 to 4 per meter square cost. I don't know how achievable this is. It seems a little bit pricier to me because right now, even if you do a square foot here in the US, just whatever you want to buy material, it's very expensive. So there's definitely some price, but it's, I don't know, it might pencil out for certain locations or applications, right? And so what we're doing is we measured various setups, locations of this white material on the ground and saw the gain and model that. And we're getting pretty good agreement between the models and the measurements, right? So that is the gain of having the reflector versus modules that don't have the reflector, because we have every module on those rows being measured. Okay, cool. So some other cool applications, thinking about applications by Wi-Fi PV that we have tested at NREL and that are also being tested worldwide, and there's a lot of interest, is agri PV. We have a section for the albedo material testing, obviously reference cells and reference areas for most of the rows. And we have added crop production and pollinator habitat and pasture grasses, as well as controls outside, right? Because you always want to, when you're doing an experiment, it's always relevant to have a control, right? Just as the albedo we're measuring up here. So to give you a little bit of more details into what we did last year, which was, I think, very successful, is we planted like 8 different crops and they grew up very nicely between the rows. And what we did was measure. There was a lot of measuring of leeks and carrots. And in general, they did just as well as the control ones, which I guess the one that did better was basil, because when it was not shaded, it started flowering because of the stress outside on the control one. So inside, it was doing awesome and growing a lot. The other ones did exactly the same, which is actually good, right? So you want it to collocate and not be worse. So being good is good. There was no bifacial gain, but the collocation was successful both for the plants and the PV. Now, in terms of modeling for agri-PV, we have used a ray trace a lot to model specific geometries for the agri-PV sites, because they tend to be a lot more custom, sometimes like with more space in between the rows. Like they have different priorities instead of just packing as many kilowatts as you can on the same area. So we have this ray trace. One thing that we will be presenting at PVSC is a comparison between the ray trace and the view factor model that I showed that's on SAM, right? That it was giving us all those growing irradiance values. So we have a validation going on for that using the whole US data, right? And I guess not to go too deep into it, but it is the irradiance, I guess, the way that we are. There's various things to report when you're modeling irradiance on the ground. One is, I guess, the average irradiance between underneath the panels or between the panels, so where there's no panels. The other option is having beds. So like in this image here, this is what's, hey, why did it move? This is what's underneath the module. And this here are 3 will be crop beds. And that allows us to say, this is the average on this month for the whole US. So anyways. I did want to touch very briefly on reliability, and that is because we have a lot of new cell technologies, right? We're really pushing the boundaries of what we can do with cells. And that's why we're seeing a lot of new effects, the LID, the LETID, etc. In terms of standards, that was actually one that passed really fast. So that people were very impressed with that. But in general, bifacial cells technology, having glass modules is not new, but some of the bifacial cells development that have enabled this explosion of the market are a little bit obviously newer, right, on the field. at least on our field, we have technology from 2019. So that's earlier bifacial technology now. A lot of those issues have been solved, like the boron doping, causing the LID, etc. But we were seeing back then double the degradation in the monofacial system. So that is kind of a little bit concerning, but we don't know, or we don't think that this might still hold for what's really going into big production now. But still, it is a big area of research and modeling of the degradation and of trying to predict how that's going, right? And this is because there is various things that vary between a monofacial and a bifacial, from the industry experience not being that much, the mechanical aspects, and in general, how the bill of material interact with each other, right? For example, the encapsulation is switching. It was EVA before, and now it's EVA POE mix or other options. So lots of information on the slide. I will share the slides, by the way, later in the week with Christopher. But the important part of reliability, and going back to the beginning, is for deployment goals for the US, for the world, this is the US one, is that we want to deploy a lot of PV, and we kind of need to not only deploy it, but have it stay in the field and keep on producing that power and not degrade and not die. So if we have modules that actually die really fast, we will like fall short from that goals that we have, right? So that is an important concept as we explore other technologies that might be coming, silicon tandem, perovskite, to really aim to make this transition, to stay on the field, install it once, and have it last as long as possible. Cool. My summary slide, yay, I made it in 46 minutes. So things that we have learned today, bifacial PV is mainstream, right? Yeah, it is mainstream, and it's going to increase with a lot of installed projects. And there's basically three main cell designs: PERC, silicon heterojunction, and TOPCon. Bifacial gain is a tricky metric, right? It can be on irradiance and on energy. It can be instantaneous, orally, weekly, yearly. And it can also be reported for just one cell, just one module, or a steady state, right? So whenever you're reading those papers that claim 50% bifacial gain, make sure that you look into those details, right? There are two main flavors of optical modeling. They are mostly converging. There's a lot of view factors. Everybody now has their view factor. And there are correction factors that you can calculate and you can apply to also match the results. And that's where a lot of the research now is going into, those correction factors. I went over how to read a data sheet, a little bit of how the standards translate to what you might actually see on that data sheet, right? I skipped a little bit on the module measurements because George covered that pretty well. Now, rear radius measurements are very important for modeling, right? And for modeling, for capacity testing, and for knowing if your performance is where it should be at. And now the standards are not finished on how and where to place those sensors, but I share some common practices and findings. Will reflectors be affected by soiling? Definitely. George, I'll get to your question in a second. Completely sorry, I get distracted by the chat, by the Q&A. Finishing the last 2 points of the learning. Cost-effective albedo enhancement is possible, and agri-PV bifacial is opening attractive possibilities for dual land use. So we are on the academia. We don't get to perhaps talk too much for industry people that are trying to deploy PV and face some, at least in the US, some pushback, right? Because people really care about the land and have misconceptions or about the importance. So agri-PV is a good way to a lot of times get deployment approved. So it's interesting from the perspective of learning and teaching and getting all of the stakeholders to agree on the importance of renewables. And the last point that I made was the reliability is key for decarbonization. And here is a little shout out to the next event that Christopher is organizing, where I will go a lot deeper into that circular economy aspects of PV. That is coming on June 7th. But answering George's question, so George asked, will reflectors be affected by soiling? Yes. So you could see on my images of the reflectors that we had that there were like a lot of patches. So actually, let's go back to that. So the way that we measure or try to account for the soiling, right, is we had those little circles all over the material. And so we will take handheld reflectometer measurements. I will not say every day, but definitely every like 4 days or so. So we keep track of how it has degraded due to soiling. So that is one big consideration, the reliability of the soilings and the sustainability as well. Like if they are going to have trouble keeping the water on the top, making water runoffs, being toxic for the animals. So I don't know, people are trying to advocate for the various products saying they are, but there's not a lot of like knowledge regarding sustainability. And yes, regarding planting permissions, maybe easier with pollinators or reflectors. Yes, it's really cute. We haven't found, I guess, pollinators with white flowers. You know, the increase on the albedo falls on the noise. Again, to some extent, the rear radiance multiplied by the officiality factor and this angular effects and the flowers not being so widespread. A lot of the times the gain falls on the noise, but it's definitely very great for the environment to have the pollinators and to collocate. I have heard though that yeah, it's an easy way to also do some sort of dual use PV on sites, on retrofitting sites, right, that are already placed. Perhaps doing crops is not as convenient, but maybe doing something like just spreading some seeds that will grow without water, right? It's nice. Anyway, Tess, questions?
Brilliant. Thank you, Silvana. I had a quick question on for comparing view factor models like that used in SAM and your ray trace one in bifacial radiance. How close are they when you model them, for example, in the 75 kilowatt system you have at NREL? How close is the data when modeled compared to measured?
So we have seen that they fall around 4% relative. I guess that's what our publication says, 4% of difference. The view factors tend to underpredict because they're assuming this isotropic sky and isotropic ground reflection, right? So when you have the sun very directly shining here, like you can see on my image here, like there's definitely some glare happening, right? So that doesn't get captured. Did I want to say about this?
So would you, yeah.
Yeah.
I was going to say, would you recommend one approach over the other under certain circumstances? Are there certain circumstances where you would say ray tracing might outperform it in terms of being more accurate to the experimental setup, or actually it's better to go with that view factor approach because you're not going to actually get much gain by doing the ray tracing?
I think it depends what you're trying to do, right? Definitely the ray trace has been shown even by third parties to be more accurate, right? It has a lot more nuts and bolts. It's also more complicated and more demanding. What I see as the job of ray tracing on the bifacial community and work now is to be used to validate and come up with methods or models, simplified models that can be used to fine tune or view factor modeling, right? So those loss factors to understand certain other effects like spectral effects and how much they may or may not impact our modeling, right? So it's a understanding a lot of those boundary conditions and effects.
So on the spectral modeling, is it possible then, can you specify the wavelength that you use in bifacial radiance?
Yeah.
How is okay, you can put down and run it for different lambda.
Mm-hmm. So the ray tracer is agnostic to what wavelength it is. It's by default set to something that's an RGB-ish thing, but we at least on bifacial radiance we have a module class that can handle spectral simulations. So uses PySmarts. So that is Smarts is a it's a Fortran code that will calculate the irradiance on any surface, right? And albedo, actually, it also gives you albedos. So because it's one of the challenges of Model Inspector is that it's hard to measure and there's not a lot of data. Just moving slightly the sensor already like gives you a lot of garbage sometimes. Sorry, so yes, we use PySmarts in conjunction with bifacial irradiance to rate trace. So yeah, that is something that I will be happy to send you to some of the things that we've done on that area to you or anybody else interested.
Brilliant. Yeah, that'd be very, very interesting for us for sure. I think there's one more question. I think that's from Yazan as well. Hi, Silvana, quick question. I'd like to inquire about the uncertainty associated with using pyranometers as albedo meters. I have concerns about the uncertainty of the reflective horizontal irradiance due to the low irradiance. I've come across research that proposes the use of reference cells as the reflective horizontal irradiance along with a pyranometer to measure GHI in some sort of hybrid albedo meter. Interested to hear your opinions on this approach.
Okay, so yes, pyranometers are widely used in the field. That's what you probably will go find on industry sites because they're cheap, right? And they have a lot of modules, so it's very easy to go and get one of this and deploy them. The difference though, well, it's been shown that they tend to drift with time, right? So for scientific research purposes, you might want something that's more stable or keep calibrating them more often, which then becomes an extra source of uncertainty in your modeling, right? They also have a very different angle of incidence than modules. That is why I guess I prefer to use reference cells for re-irradiance because they have the same angle of incidence and they have the same spectral responsivity because they're silicon to the panels, right? So you already like knock off two of the uncertainty sources by using a reference cell. In terms of the albedometer, I think the guidance is usually to use a broadband one though, right? When you're modeling, you are assuming broadband sky, broadband DNI and broadband DHI, not just the spectrum responsivity component that the PV will like. So because of that, you're also at that stage still using a broadband sensor. So pyranometers are broadband, so that's great. CM11s or CM22s, so like a higher quality pyranometer will be much better. So those definitely tend to drift less, but they're more expensive. Regarding hybrid albedometers, I have not read about that, but gosh, you're making it very complicated now.
Yeah, we've seen some work with pyranometer for the POA and a reference cell for the BOA as an approach for the albedo meter. Just because of the low light levels that the pyranometers are facing.
Yeah. Well, we have I guess, what is this? I guess you can go and look at the bifacial data that we have on our site. That's all open source because we give the POA and the BOA for the three albedometers that we have side to side, which is the reference cell, regular pyranometer, and a CM11. I have not used as a denominator a different modeled or referenced than the numerator. But yeah, I don't know if that will actually give you something. What I can tell you is that there is definitely a lot of difference when snow covers them because the reference cell tends to keep snow a lot longer. And there are some differences also, I guess, through the day between the three sensors. So that's an interesting area.
Brilliant, thank you. I think there was a question. I think this is just to clarify a common question on bifacial cells and two monofacials back to back. Just clarifying where's the difference between the two monofacial solar cells back to back and a bifacial cell.
I not seen two monofacials back to back. That's not how we are producing PERC cells. I get asked this sometimes, like, well, can I just put one monofacial facing this way and one monofacial facing that way? So you're doubling your costs, right? If you're doing that versus having one module that already does both. And the module will definitely, the back will not be as effective as the front, but I mean, 70% of the front at the same cost is great. So I don't, yeah. That's not how the cells are being produced right now, at least.
Yeah, so the bifacial is just opening up that back metal to allow irradiance again on the rear side, rather than trying to go back to back. A question from George: have you considered linearity issues with commercially available irradiance sensors for rear side irradiance measurements, especially under low irradiance levels? And that will be the last question. Silvana.
Have I considered? I don't study that much. But definitely what we have done on when we use the sensors, the re-radiance sensors on the LB, is calculate the uncertainty. And with the low levels, usually the models fall underneath the uncertainty. Because you have irradiances of below 100 watts per meter square. And if you go to the data sheets of a referencer or of a pyranometer, like it really increases the uncertainty level of the measurements. So I don't know if that answers that properly, but.
Brilliant. Thank you very much, Silvana. I think a few more questions are coming through to the Q&As. If you do have some time, please try and respond to those. But thank you very much for your talk today. I'd also like to thank all the speakers from this morning and this afternoon for their time and for their talks. It's been very informative, and we've had lots of questions coming in. I think this recording is this talk has all been recorded, which I think, Chris, we can share that if on request. Is that right?
Yeah, I'll be sharing the recording via the Supersolar website. So I'll usually get that up a few days afterwards, but I've got some holiday next week, so it will probably not be next week, maybe a couple of weeks. If people want to come back and have a look on the Supersolar website, there'll be a little post about the recordings being available there.
Brilliant. What we'll do is we'll put the link for the Supersolar website onto the chat. I'll also put the link to the PVSat conference website as well. So please do look at both and register. And thank you all very much for attending. Thank you. Bye.